Alright, whether you're in bed, driving, or quietly orbiting your own thoughts, this one's for the sapiens who still can't sleep. If you enjoy these slow dives into the science that built us, remember to support this project with a like and subscribe. It keeps long-form storytelling alive for curious minds like yours. Now, look up. The thing that made you possible is still burning. For most of human history, the sun was simply a fact, not a mystery. It rose, it set, and in between it was life. We treated it as steady, the one constant against our chaos. Even now, with satellites and space telescopes and megabytes of solar data, it's easy to forget that the star we orbit isn't a lamp. It's a storm, one that just happens to look calm from 93 million miles away. So here's the question that quietly humbles every astronomer. What does it mean that the sun has a heartbeat of its own? We're used to thinking of living things as things that breathe, things that pulse. But stars, it turns out, do something similar. They swell and contract, flare and fall silent, all according to internal rhythms we've only recently learned to measure. When early astronomers began sketching the sun in the 17th century, they noticed something peculiar. Across its blinding face, through filters and projection tubes, they saw dark stains appear, vanish, and then appear again. Sunspots. To the human eye, they looked like imperfections. To science, they were the first clues that the sun was not an unchanging disk, but a restless sphere of plasma, boiling under its own gravity. Each sunspot was a magnetic wound. It marked a place where magnetic fields twisted so tightly they blocked some of the heat escaping from below. The spots were darker only because they were slightly cooler, about 4,000 degrees instead of 6,000. Still bright enough to incinerate any human definition of cool over days or weeks. These marks drifted across the solar surface, grew, merged, and dissolved. Then, after a few years, the spots became scarcer. A few years more, and they multiplied again. By the early 19th century, a German apothecary named Heinrich Schwabe, who spent 17 years obsessively sketching the sun every clear morning, realized he was seeing a pattern. The number of sunspots waxed and waned roughly every 11 years. That discovery, the Schwabe cycle, changed our understanding of the star that powers every breath on Earth. For the first time, the sun had a pulse. Schwabe's quiet dedication, done through a small telescope from his backyard, revealed that what looks eternal from our scale actually moves to its own clock. It's not a perfect metronome. Sometimes the cycle is 10 years, sometimes 13. Sometimes the sun grows so quiet it barely registers a pulse at all, a deep solar sleep called a minimum. Other times, the surface seethes with activity, throwing off flares and storms in a kind of luminous fever, a solar maximum. At its heart, the cause is magnetic. Deep within the sun, hydrogen atoms collide under immense pressure, fusing into helium and releasing energy as light. The plasma churns in convection cells the size of continents, and that motion, combined with the sun's rotation, acts like a gigantic dynamo. Magnetic field lines stretch, twist, and occasionally snap, releasing vast amounts of energy. Each 11-year cycle marks the time it takes for these tangled magnetic threads to reorganize themselves. When they get most knotted, the sun bursts into heightened activity, and when they unwind, the surface calms. But here's where the rhythm gets even stranger. Every time the sun reaches one of its peaks, its magnetic poles flip. North becomes south, south becomes north. This happens not once, but every other cycle, meaning that a full magnetic oscillation, from one polarity and back again, takes roughly 22 years. That longer pattern is known as the Hale cycle, after George Ellery Hale, the American astronomer who confirmed the sun's magnetism in the early 20th century, using spectroscopic fingerprints of iron. The Schwabe cycle is the sun's visible pulse, the Hale cycle is its deeper breath. From Earth, we can't see this polarity change directly, but the sun's atmosphere feels it profoundly. Magnetic loops arc above the surface, trapping plasma and snapping back like elastic bands. When they break, they release coronal mass ejections, titanic bubbles of charged particles flung across space at millions of kilometers per hour. The corona itself, that ghostly outer atmosphere visible only during eclipses, responds by brightening and spreading. To us, it seems like poetic chaos. To the sun, it's simply its natural way of reorganizing. Think of it as a magnetic pendulum made of fire. The energy doesn't disappear, it oscillates between order and disorder. At solar minimum, the field lines run neatly from pole to pole, a quiet global structure. By solar maximum, they've become a tangled web, wrapping around each other until tension forces them to realign. Then the pattern begins again. It's a system that seems alive, yet it's entirely mechanical. Physics performed at cosmic scale. Scientists have been recording these cycles for just over 2 centuries, but their influence can be traced much further back. In the isotopes of ancient ice and tree rings, subtle variations in carbon and beryllium reveal periods when the sun was less active, its magnetic field weaker, allowing more cosmic radiation to reach Earth. One famous example is the Maunder minimum between the years 1645 and 1715, when sunspots nearly vanished for 70 years. Europe, during that same period, endured colder winters and failing crops, a reminder that even a small change in solar mood can ripple through climate systems. Yet even then, the sun wasn't truly dormant. It was merely at the low end of its natural cycle, catching its breath. Today, we monitor that breath with spacecraft like 𝐓𝐈𝐌𝐄𝐒𝐒 and the Parker Solar Probe, instruments orbiting closer to the sun than anything before. They watch it not as worshippers, but as students trying to decode its patterns. We've learned that the sun's outer atmosphere, the corona, is paradoxically hundreds of times hotter than its surface, though we still don't know why. We've mapped magnetic loops that dwarf planets and tracked plasma waves that ring through the sun like sound through a bell. And yet, after all this, we still can't fully explain why the Schwaber cycle lasts roughly 11 years, and not 8, or 14, or 50. Some have pointed to Jupiter's orbit, conveniently similar in length, as a possible influence, a gravitational nudge sinking the solar dynamo. But the data don't quite fit. The sun's rhythm, for now, remains its own secret. There is something quietly humbling about that. Humanity has built machines that can peer into atoms and out beyond galaxies, yet the most important star to our survival still keeps mysteries hidden in plain sight. Each dawn we're reminded of it, though we rarely notice. The same light that paints your morning coffee is shaped by nuclear reactions that began millions of years ago. Photons that have fought their way through dense plasma, bouncing and scattering until finally escaping into space and landing on your skin. The warmth you feel is a story that started long before language, a story that pulses in cycles we can sense only through patience. What's remarkable is how steady this chaos feels from our perspective. While our own history swings through wars, extinctions and empires, the sun's rise and fall of magnetism continues, indifferent and dependable. It's been beating like this since before Earth cooled, since before the word year meant anything. Each flare, each dark patch, each 11-year sigh is part of a rhythm older than continents. Right now, as you listen, the sun is moving toward its next maximum, expected around the middle of this decade. Already, sunspots are multiplying, and magnetic activity is ramping up. In a few years, the solar surface will look more like a lava sea than a serene sphere. It's beautiful, but it's also a reminder that serenity can be an illusion of distance. If our eyes could perceive magnetic energy instead of light, the sun would look less like a ball of gold, and more like a living organism constantly shifting its skin. Scientists often talk about the sun as a laboratory, a place to study plasma physics, nuclear fusion, and magnetism at scales impossible to reproduce on Earth. But there's something almost personal about it too. Its cycles set the tempo of our seasons, shape our sky's colour, and even influence the faint whispers of the aurora that wrap the poles in green. We exist inside its atmosphere, within its extended magnetic bubble known as the heliosphere. Our world is not separate from the sun, it is one of its layers, and yet for all this intimacy, we are still guessing at causes. What drives the 11-year pulse? Why does the corona flare so unpredictably? What makes one cycle mild and the next violent? There are models, equations, computer simulations that fill entire observatories with data, but the truth is that the sun remains partly unknowable. Its heart is hidden under 500,000 kilometres of incandescent gas, and our best instruments can only infer its movements through oscillations and surface ripples. Like listening to a heartbeat through a wall, we hear the rhythm but not the reason. Still, there is comfort in that mystery. The sun's imperfection is the reason life exists at all. If it were perfectly steady, perfectly silent, our planet might have been sterile. Its minor fluctuations, its magnetic quirks and flickers, have shaped Earth's climate and atmosphere in subtle ways over billions of years. Stability, it seems, doesn't come from stillness but from balance, a dance between order and chaos, repetition and change. When you think about it, the idea that our star breathes isn't poetic exaggeration, it's literal physics. Energy flows outward, fields reverse, plasma circulates. A cosmic inhale, a cosmic exhale. The rhythm is slow, patient, unhurried. In that sense, perhaps the sun is teaching us something, that even the most powerful things in the universe spend half their time gathering energy before they shine again. And as we move toward the next solar peak, with instruments poised and scientists waiting for new data, the question remains not just what the sun will do, but what we will learn from it this time. The heart of our solar system beats on, indifferent to our attention, and we, small and curious, keep listening for the next pulse. All right, whether you're walking home under the evening glow or letting this play you to sleep, take a quiet moment to remember that soft sunlight on your skin is also one of the most dangerous forces in the solar system. It only seems gentle because 93 million miles of distance act as the universe's most effective safety barrier. But what if one day that barrier isn't enough? What if sunlight could knock out the internet? It sounds absurd at first. The same light that feeds plants and keeps us alive. The light that paints everything we've ever seen, turning against the very civilization it helped build. Yet that's not science fiction. It's a documented possibility, and one that has already brushed against us more than once. To understand how, we need to travel back to a morning in early September of the year 1859, when the sky itself decided to interfere with technology for the first time. It began with light, but not the kind that comforts. In London, an astronomer named Richard Carrington was observing the sun through a filtered telescope when he noticed an enormous burst of brightness near a cluster of sunspots. It flared for less than a minute. Carrington had no way of knowing that this tiny event would soon unleash one of the largest geomagnetic storms in recorded history. A day later, the night sky erupted. People across North America and Europe looked up to see auroras shimmering as far south as the Caribbean. Miners in the Rocky Mountains thought it was dawn and began making breakfast. Telegraph operators, working late into the night, reported electric sparks leaping from their equipment. In some offices, the telegraph systems continued to transmit even after the power had been cut, fueled by invisible currents racing through the Earth itself. That event became known as the Carrington event, and its legacy remains the gold standard for what we fear from solar storms. What Carrington had unknowingly witnessed was a coronal mass ejection, a vast bubble of charged particles and magnetic fields hurled into space from the sun's atmosphere. When such a cloud reaches Earth, it can compress the planet's magnetic field, causing it to ripple and twist. The result is a geomagnetic storm, electricity where electricity shouldn't be, energy invisible but lethal to circuits, satellites and long cables that span continents. In the 19th century, the world's technology was relatively simple. Telegraphs could spark and still recover. Today, our power grids, satellites and global communications are far more vulnerable. In March of 1989, another powerful solar storm struck Earth. This time, it hit a modern electrical network, the Hydro-Quebec system in Canada. Within 90 seconds, the entire grid collapsed. 6 million people lost power in the middle of winter. The blackout lasted 9 hours, disrupting everything from heating to radio communications. The cause wasn't sabotage, and it wasn't technical failure. It was the sky. The same geomagnetic surge that once lit up telegraph lines in Carrington's day had found a new path through high-voltage transmission cables, generating currents strong enough to blow transformers. Events like this are reminders that our planet's magnetic field is not a solid wall. It's more like an elastic bubble, the magnetosphere, surrounding Earth and deflecting most solar particles. Under normal circumstances, it shields us beautifully. But when a coronal mass ejection slams into it, the magnetosphere vibrates like a struck drum, and those vibrations induce electric currents in the ground. Long metal structures like pipelines and power lines act as antennas, channeling that energy where it was never meant to go. The danger isn't the light you see, it's the storm hidden inside it. When we talk about space weather, what we really mean are these interactions, the dance of magnetic fields and charged plasma between our sun and our planet. Unlike rain or wind, space weather can't be felt directly. You don't need to look out a window to know it's happening. Instead, scientists monitor the sun's activity through satellites, watching for flares and eruptions. When a major event occurs, they can estimate how long it will take to reach Earth, sometimes as little as 15 hours. It's a strange feeling to know that our entire technological civilization now depends on space weather forecasts. A single, high-speed coronal mass ejection, if aligned just right, could disrupt global positioning systems, knock satellites out of orbit, and trigger widespread power failures. Even the internet, that invisible web we treat as eternal, runs through networks of undersea cables connected to ground-based power grids. If enough transformers were damaged at once, recovery could take weeks or even months. To most of us, solar storms are invisible, but astronauts aboard the International Space Station see their effects firsthand. When a burst of charged particles hits Earth's magnetic field, auroras bloom like ghostly curtains near the poles. The colours we see, green, red, violet, are the atmospheric gases fluorescing under bombardment. But beauty comes with risk. Astronauts must retreat to shielded sections of the station during major events, as radiation levels can spike far beyond safe limits. Satellites too go into protective standby modes to avoid being fried by electrical surges. The same principle applies in orbit as on the ground. Too much current, too fast, and fragile electronics melt. In low Earth orbit, where most satellites reside, even a minor increase in atmospheric drag can be disastrous. When solar storms heat the upper atmosphere, it expands outward slightly, increasing friction. A few hundred extra molecules per cubic centimetre may not sound like much, but it's enough to slow satellites down. In the year 1989, that expansion caused several spacecraft to lose altitude and in some cases burn up on re-entry. It's ironic that one of them was a solar observatory built to study the very flares that destroyed it. Because of these risks, agencies like NASA and the European Space Agency now operate continuous monitoring programs. The Solar Dynamics Observatory and the Parker Solar Probe track changes in solar radiation and plasma flow, sending data back in real time. The goal is simple: warning. A 24-hour notice can be the difference between shutting down a satellite safely and watching it fail. Power companies too use these forecasts to adjust loads and protect transformers when a storm is incoming. It's a global choreography between human technology and the ancient physics of a star. And yet, for all our instruments and models, we can't predict the sun with perfect accuracy. Each coronal mass ejection is unique, shaped by magnetic fields that twist in ways no computer can fully capture. Some storms, like the Carrington event, are extreme outliers, the once-in-a-century catastrophes. But smaller ones happen constantly. They ripple through our magnetosphere every few days, barely noticed except by scientists. In that sense, Earth lives inside a constant drizzle of solar weather, punctuated occasionally by hurricanes. Every few decades, though, the probabilities align for something bigger. Studies of tree rings and polar ice show traces of even stronger storms in the past, far beyond what we've recorded since the industrial era. If an event on the scale of the Carrington storm happened today, estimates suggest it could cause trillions in damage. Some researchers have nicknamed it the Internet Apocalypse scenario, a solar storm capable of knocking out communication satellites, corrupting GPS networks, and overloading global power grids all at once. The name sounds dramatic, but the physics is soberly real. What's strange is how personal it feels when you think about it. A flare on the sun's surface, born from tangled magnetic lines thousands of kilometers long, could one day ripple across the void and shut down your favorite streaming service. The light you see from the sun takes 8 minutes to reach Earth. The charged particles from a coronal mass ejection take between 15 hours and 2 days. That means when you read about a solar storm approaching, you're living in a kind of slow-motion suspense. light from the flare already bathing Earth in brilliance, while the storm itself races invisibly behind it. It's the only natural disaster that announces itself with a sunrise. There's a quiet humour in that. Newspapers once published daily horoscopes promising that the stars influence your destiny. In a way, they weren't entirely wrong, just off by a few million degrees. The sun does influence us, not in mystical ways, but through the hard physics of electromagnetism. If your GPS drifts, or your power flickers during the next solar maximum, you can blame your horoscope, the real one, written in plasma instead of prose. We might wonder how often we can expect such disturbances. The good news is that truly catastrophic storms are rare. The less comforting part is that rarity doesn't mean immunity. The sun's current cycle, heading toward its peak around the middle of this decade, has already shown signs of higher than average activity. In recent months, solar observatories have recorded multiple X-class flares, the most energetic category, and complex sunspot groups sprawling across the surface. For space agencies, that means heightened alertness. For everyone else, it means brighter auroras and a little more uncertainty in the systems we take for granted. Still, there's something almost poetic about how interconnected it all is. The same charged particles that threaten satellites also paint the polar skies. The same physics that powers city grids also powers solar storms. The beauty and the danger are inseparable, two sides of one process. Perhaps that's the truest character of sunlight. It creates and it destroys, it enlightens and it erases. The photons that built civilization can, in the right configuration, remind us how fragile civilization really is. We often think of natural disasters as earthbound things, earthquakes, hurricanes, floods. But geomagnetic storms remind us that our planet's weather doesn't stop at the atmosphere. It extends into space, shaped by forces far older and larger than us. Space weather is a term that sounds small, almost bureaucratic, yet it describes the frontier between a living planet and a living star. It's a reminder that we are still learning to coexist with the very energy that sustains us. The next time you see an aurora photograph shared online glowing over some frozen northern lake, remember that you're looking at both art and warning. Those lights trace magnetic chaos made visible, a pulse of solar activity reaching across space to touch our world. They are postcards from the sun's moods, reminders that even light can have tempers. Maybe that's the lesson hidden in all this, that civilization's progress hasn't insulated us from nature. It has only connected us to it in new, more fragile ways. A burst of plasma from a star, born before humans existed, can still flicker through our screens. The universe is vast, unpredictable, and occasionally inconvenient, and yet somehow, beautifully, it keeps us humble. Imagine this. Above you, around you, and beneath your feet, something ancient and invisible is still working to keep you alive. It hums in silence, made of molten metal and motion. Every compass needle ever made is just an echo of it, and yet you've never seen it. The question is simple. What happens if Earth's invisible shield falters? To understand what's keeping us safe, we have to dig far deeper than any drill can reach, back into the planet's heart. About 4.5 billion years ago, Earth was not the calm blue sphere we know. It was molten, a spinning mass of rock and metal slowly cooling in the shadow of a violent young sun. Heavy elements like iron and nickel sank inward, while lighter materials floated upward to form the crust. In that slow separation, the planet built something extraordinary, a metallic heart that still beats today. The outer core, roughly 2,000 kilometers thick, remains liquid iron alloy, swirling and churning like an ocean of molten metal. Beneath it lies a smaller solid core about the size of the moon, compressed so tightly that despite its immense temperature, it stays frozen in place by pressure. This arrangement, a solid heart inside a liquid sea, creates what scientists call the geodynamo. The heat from the inner core escapes upward, setting the liquid metal in motion. Because the Earth spins, those motions twist into spirals, generating electrical currents on a planetary scale, and wherever electricity moves, magnetism follows. The magnetic field that results extends far into space, forming an invisible cocoon around our planet. Without it, we might look a lot like Mars, dry, exposed, stripped of atmosphere. That's not poetic exaggeration. It's physics. Billions of years ago, both Earth and Mars had molten cores and magnetic fields. But as Mars cooled more quickly, its dynamo died and its protective field faded. Without that magnetic shield, the solar wind, a continuous stream of charged particles from the sun, began to erode its atmosphere, molecule by molecule, until what remained was a thin, breathless whisper. Earth avoided that fate because its core stayed hot. Part of that heat came from the slow crystallization of the inner core, releasing latent energy the way freezing water releases heat. Another part came from radioactive decay of elements like uranium and thorium trapped inside. This steady supply of energy keeps the outer core fluid, and the fluid keeps moving, maintaining the dynamo. It's a feedback loop millions of years in the making. When we say the magnetic field protects us, it's not just metaphor. The field intercepts charged particles that stream from the sun, steering them away from the surface and into spiraling paths around the poles. Those deflected particles are what create the auroras, glowing veils of light where the field lines dip into the atmosphere. But most of the solar radiation never gets that far. The magnetosphere acts like a planetary force field, diverting and trapping dangerous particles in vast belts that circle the planet. These are the Van Allen radiation belts, discovered in the middle of the 20th century, when the first satellites began sending back data. They mark the invisible boundaries of our world's magnetic armour. What's remarkable is that this shield is both immense and fragile. At ground level, the magnetic field is weak enough to barely nudge a compass needle, but in space, it's strong enough to deflect storms of plasma thousands of kilometres wide. It's like protecting a house with a soap bubble that happens to be perfectly placed, and that bubble is constantly changing. The magnetic field isn't static. It shifts, wobbles, and sometimes weakens. On the timescale of human lives, we might never notice. But in geological time, it's restless. We know this from ancient rocks. When molten lava cools, minerals rich in iron align themselves with the Earth's magnetic field like tiny compass needles. Once the rock solidifies, those alignments freeze in place, preserving the direction and strength of the field at that moment. By analysing the magnetic patterns in ancient lava flows and ocean sediments, scientists have reconstructed a history of the field, stretching back hundreds of millions of years. What they found is extraordinary. The magnetic poles have wandered, drifted, and even swapped places entirely many times. Full reversals of north and south occur irregularly, roughly every few 100,000 years, although there's no strict schedule. The most recent major reversal, known as the Brunhes-Matuyama reversal, happened about 780,000 years ago, long before Homo sapiens existed. There have been shorter, incomplete reversals too, what geophysicists call excursions, brief failures in stability where the field weakens and the poles roam before snapping back. These events remind us that the magnetic field isn't carved in stone. It's an ongoing conversation between liquid metal and motion. One of the most intriguing pieces of evidence for the field's imperfection today lies in a region called the South Atlantic Anomaly. It stretches roughly from South America to southern Africa, and it's where the magnetic field dips closer to the Earth's surface than anywhere else. This creates a kind of magnetic valley where radiation levels are slightly higher. Satellites passing through it often experience glitches or need to be powered down briefly to protect their electronics. To us, that may sound like a modern technical nuisance, but geologically speaking, it could be the early sign of another rearrangement deep within the core. Scientists studying this anomaly have found that the field there has been weakening over the past few centuries. It's as if the outer core's circulation has shifted, causing magnetic lines to cancel out rather than reinforce each other. Whether this is the start of a true reversal or just a long fluctuation, no one can yet say. What we do know is that the magnetic field strength has dropped by about 10% in the last 2,000 years. Not catastrophic, but noticeable on planetary timescales. If the field were to weaken significantly, Earth wouldn't suddenly lose its protection overnight. Even during reversals, the field doesn't vanish entirely. It becomes complex, with multiple north and south poles forming in odd places before stabilizing again. The atmosphere would still shield us from most radiation, and life has survived countless reversals before. But the process could make our magnetosphere patchier, allowing more high-energy particles to reach the surface. In deep time, that might subtly influence mutation rates or atmospheric chemistry. What's most striking about studying the magnetic field is how ancient it is, and how early it may have saved us. Evidence suggests that Earth's dynamo has been running for at least 3.5 billion years. That means the magnetic field was already active when life first began to appear in the oceans. Some researchers even think the field played a role in that origin story, protecting early organic molecules from being destroyed by solar radiation. Without it, ultraviolet light and cosmic rays might have sterilized the planet's surface before life had a chance to stabilize. We can see hints of this protective history in planetary comparisons. Mercury, the smallest terrestrial planet, still has a weak magnetic field, but its proximity to the Sun exposes it to harsh radiation. Venus, though similar in size to Earth, rotates too slowly to generate a strong dynamo. It has almost no magnetic shield and suffers from a superheated, corrosive atmosphere. And Mars, once magnetic, lost its shield long ago and with it much of its air and water. Earth stands alone among the rocky planets as a place where magnetism and habitability have persisted hand in hand for billions of years. It's easy to overlook how fragile that balance is. The entire geodynamo depends on a few critical conditions: a liquid outer core, a solid inner core, and enough rotation to keep the flow organized. If the core cooled too much, if convection slowed, or if some massive event disrupted the pattern, the field could decay. In fact, Earth's magnetic intensity has fluctuated dramatically in the past. During certain intervals, it has fallen to a fraction of its current strength before recovering again. These are the planet's slow heartbeats, variations that take hundreds of thousands of years, invisible to the civilizations that rise and fall on its surface. Scientists studying seismic waves use them to peer into the core and monitor its evolution. They've discovered that the inner core is slowly growing as the planet cools, solidifying at a rate of 1 millimeter or 2 per year. Paradoxically, that growth may strengthen the dynamo by releasing heat and light elements into the surrounding liquid iron, keeping the circulation alive. So far, Earth's magnetic heart shows no sign of stopping. But one day, billions of years from now, when the core finally solidifies completely, the field will fade. By then, the Sun will have swollen into a red giant, and the story of magnetic protection will be long over. Until then, we live within this invisible grace. Every compass, every migrating bird, every aurora is a quiet signature of that ancient machine still running beneath our feet. The next time you hold a magnet in your hand, consider that it's not a human invention, but an echo of the planet's deep interior. It's the same force that once guided the first sailors, that still guides whales through the open ocean, and that has guided life through billions of years of cosmic radiation. And if you ever wonder what happens when that shield falters, look again at Mars, dry, red, and exposed. It's a glimpse of an alternate history, a version of Earth that lost its magnetic heartbeat. Our world remains alive not just because of sunlight or water or air, but because a sea of molten metal still stirs in the dark. For all our technology, we owe our survival to something utterly primal, the quiet spinning of iron deep below, keeping the sky intact. Whether you're listening in the dark or watching the sky without realizing it, somewhere above you the planet's magnetic field is quietly shifting. It's invisible, slow, and ancient, but lately, something about its rhythm has changed. North is moving, not metaphorically but literally. Every few months magnetic north slides a little farther towards Siberia. The poles are migrating faster than at any other time in recorded history, which raises a question humans love to ask but dread to answer. Are we overdue for a flip of the poles? The first time anyone realized that Earth's magnetism wasn't stable forever was only a century ago. Before that, we treated the field as a permanent compass, a cosmic North Star to orient our world. But the planet's geological memory told a different story. When lava cools, iron-bearing minerals inside it align with the direction of the magnetic field, freezing tiny compass needles into stone. These magnetized rocks became the planet's hard drive, each layer a snapshot of which way north pointed when it solidified. In the 1920s, researchers studying basalt along the mid-Atlantic ridge noticed something impossible. Some rocks were magnetised in the opposite direction from today. What they had found were the fingerprints of ancient reversals, proof that north and south had swapped places many times before. We now call the most recent of these great flips the Brunnes-Matuyama reversal, after the scientist who confirmed it. It happened roughly 780,000 years ago. The magnetic field didn't simply shut down and restart like a power switch, it unravelled. Over several thousand years the poles drifted, weakened, then switched sides entirely. Compasses, if they had existed, would have spun in confusion before settling into a new orientation. Since then, the field has reversed dozens of times on average, though not at regular intervals. Sometimes the gap between reversals has been 1,000,000 years, sometimes only a few 100,000. There's no cosmic calendar dictating when it must happen again. Still, patterns whisper clues. Over the last 2 centuries, scientists have measured a steady decline in the strength of Earth's magnetic field, about 10% weaker than it was when we began keeping track. This is not catastrophic by itself, but it's faster than usual, and the current drift of the magnetic poles is accelerating. In the mid-20th century, magnetic north was somewhere in the Canadian Arctic. Now it's racing across the pole toward Russia at nearly 50 kilometers per year. For perspective, that's roughly the speed of a migrating glacier. Fast for geology, slow for daily life. So what exactly happens when north becomes south? The physics isn't mysterious, the choreography is. Deep inside the outer core, molten iron moves in giant spirals generating electric currents. When those flow patterns become disordered, the magnetic field weakens, splits into multiple smaller poles, and can eventually reconfigure with opposite polarity. During this process, the field doesn't vanish entirely, it becomes chaotic. Instead of one north and one south, the planet can briefly have half a dozen of each scattered around the globe. If you could see the field lines, they would look tangled, looping in strange asymmetrical shapes before gradually stabilizing again. For a planet's surface, the most noticeable change during a reversal isn't which direction your compass points. It's how much less protection the field provides while it reorganizes. With a weaker magnetosphere, more solar and cosmic radiation reaches the upper atmosphere. The auroras, those beautiful curtains of light normally confined to the poles, would spread toward the equator, painting skies over regions that have never seen them before. It would be an awe-inspiring sight. Shimmering greens and violets arching over deserts and rainforests, a planetary light show marking magnetic disorder. But beyond the beauty, there's also fragility. The field's strength can drop to a fraction of its normal value during a reversal. That means our upper atmosphere would absorb more high-energy particles, slightly altering its chemistry. Satellites and other technologies would feel it most, but let's leave that for later chapters. What matters here is the scale of the process. This is not an overnight catastrophe, but a slow-motion rearrangement of the planet's deep machinery. The whole transition could take thousands of years. Life on Earth, including our distant ancestors, has endured dozens of these events before. Geological records even reveal near misses, periods when the field almost flipped but didn't. These are called magnetic excursions. One of the most famous, the 𝐓𝐈𝐌𝐿 excursion, occurred around 42,000 years ago. For a brief time, the field weakened drastically, perhaps to 10% of its current strength, and magnetic north wandered far from its usual place before snapping back. Sediment cores and ice samples from that era show increased levels of isotopes like beryllium-10, evidence that more cosmic radiation reached the atmosphere. The 𝐓𝐈𝐿 event is often cited as a preview of what a full reversal might look like. Disruptive, but not apocalyptic. When scientists talk about reversals, they sometimes use the phrase overdue, but that word is misleading. There's no internal clock that demands a flip on schedule. The geodynamo is chaotic by nature, its behaviour governed by turbulent flows that can't be predicted like tides. Some periods in Earth's history saw frequent reversals, others went tens of millions of years without one. The longest known stretch of stability, called the Cretaceous Normal Superchron, lasted almost 40 million years. So if you hear someone say we're overdue, it's like saying a volcano is overdue. It's true only in hindsight. What we can say is that right now the signs of instability are real. The magnetic poles are wandering faster, the South Atlantic anomaly is growing, and the global field strength is declining. None of this guarantees an imminent reversal, but together they suggest the core's convection patterns are shifting. Seismology has revealed that parts of the outer core beneath Africa and the Pacific behave differently, perhaps setting up regions of opposing magnetic polarity that cancel each other out. Think of it as turbulence within the Earth's own bloodstream. If you could stand outside the magnetosphere and watch this process unfold over millennia, you'd see our planet's invisible aura flicker, wobble, and eventually realign. The magnetosphere's tail, stretching away from the sun like a comet's, would twist and warp as the poles traded places. In that distant, silent view, Earth would seem alive, its magnetic skin breathing in irregular rhythms. The last reversal left a permanent signature in the rocks. Around the world, lava flows from that period record the moment when the field flipped. If you line them up by age, you can almost watch the pole drift across the globe. In France, in the Auvergne volcanic region, layers of basalt preserve the magnetic direction before, during and after the Brunès-Matuyama event. It's a geological time-lapse, a stone record of north losing its sense of direction and then finding it again. There's something deeply human about our fascination with these flips. The idea of the planet turning itself inside out appeals to our love of drama. Ancient cultures often imagined world reversals as omens, times when the heavens and earth would swap roles, when chaos would temporarily rule before order returned. In a way, the magnetic reversal is the scientific version of that myth. It really does happen, just more slowly and less catastrophically than legend suggests. If myths warned that the sky would fall, science reminds us that it only shimmers differently for a while. Of course, our modern world is built around instruments that assume magnetic north is reliable. Airplane navigation, geological surveys, even smartphone compasses rely on magnetic reference data that must be updated constantly as the poles drift. In the age of apps, your compass might literally have trust issues. Each year, agencies like the British Geological Survey and the US National Centres for Environmental Information release new models to correct for the pole's movement. It's a quiet acknowledgement that our planet is always slightly rewriting its own coordinates. So, are we heading for another reversal soon? Soon, in geological terms, can mean a few thousand years or a few 100,000. The weakening field could be the prelude to a flip, or just another temporary wobble like the 𝐓𝐈𝐌𝐄𝐒𝐓𝐀𝐌𝐏𝐒 excursion. No one can say for certain. What we do know is that these magnetic dramas have played out countless times without erasing life from the planet. Even at its weakest, Earth's field has been enough to keep our atmosphere intact and our surface shielded from most radiation. The record shows disruption, not extinction. In the end, the story of magnetic reversals is less about disaster and more about perspective. It reminds us that the forces shaping our world move on scales far beyond our comprehension. While we measure time in elections and generations, the planet measures it in fluid motion and molten iron. The slow heartbeat of the core doesn't care about calendars. One day, whether 10,000 or 10 million years from now, the compass will settle on a new north. Maps will be redrawn, magnetic charts recalibrated, and the planet's story will continue as it always has. For now, the drift of the poles is a quiet reminder that even the most stable parts of our world are in motion. The invisible shield that protects us is also alive, restless, and occasionally indecisive. Perhaps that's fitting. After all, if a planet can change its mind, maybe there's hope for the rest of us too. Whether you're standing by the ocean, or just listening to the quiet in your room, somewhere right now the sea is moving because of a rock in the sky. It pulls, pauses, and pulls again, an ancient rhythm so consistent that we forget how fragile its balance is. The moon's gravity has been shaping Earth's tides for over 4 billion years, turning oceans into slow, breathing lungs. But every so often, that breath deepens. The question is, how can a 5-degree tilt drown coastlines? To understand it, picture the moon's orbit not as a perfect ring, but as a slightly tilted ellipse, about 5 degrees off the plane in which Earth circles the sun. That tilt is enough to make the moon's path wobble slowly, a gentle oscillation that takes 18.5 years to complete. This is called the lunar nodal cycle, and it's one of the quietest forces shaping life along our coasts. Every orbit, the moon crosses the plane of Earth's path twice, once heading north of it, once heading south. Those crossing points are called nodes. Over the course of nearly 19 years, The line connecting those nodes shifts, tracing a complete backward loop around the Earth. When the moon's tilt brings it slightly closer to our equatorial plane, the gravitational pull on the oceans intensifies. Tides become a little higher and lower than average. When the tilt drifts farther away, the tides flatten slightly. You don't notice it walking along a beach, but over decades this gentle wobble changes how high the water climbs with each new and full moon. During one half of the cycle, the daily high tides are modest, the low tides less extreme. During the other half, the amplifying phase, the ocean becomes more responsive to lunar gravity. It's like turning up the volume on the tides themselves. Right now, we're heading into the loud half of that cycle. The last major peak occurred around the year 2015. The next will crest between roughly 2030 and 2035. It's during these amplification periods that coastal flooding becomes more frequent, especially in areas already perched at sea level. NASA scientists studying tide gauge data noticed that when the last nodal maximum aligned with seasonal high tides and minor weather events, floods that were once rare became common enough to disrupt traffic, damage infrastructure, and reshape shorelines. To understand why, imagine how tides work on an ordinary day. The moon's gravity pulls a bulge of ocean water toward it, creating a high tide on the side of Earth facing the moon. Another bulge forms on the opposite side due to inertia, giving us a second high tide roughly 12 hours later. The sun adds its own influence, sometimes amplifying the moon's effect when both align, what we call spring tides, and sometimes muting it when they are at right angles, producing neap tides. Now, add the nodal wobble. When the moon's orbit tilts closer to the equator, it allows the tidal bulges to reach slightly farther north and south, overlapping more with populated coastlines. High tides climb just a bit higher everywhere, not enough to be noticed in a single day, but enough to make an enormous difference over decades. The amplification isn't a storm surge, it's a quiet creep, a regular tide that just happens to spill over more often. This isn't theory, it's measurement. NASA's Sea Level Change Team, combining satellite altimetry and tidal records, projects that by the early 2030s, the ongoing nodal maximum will coincide with the baseline rise of the world's oceans, a convergence that could multiply coastal flooding events several-fold. What were once a few nuisance floods each year could become near monthly, or even daily, in vulnerable regions. The change won't come as a single disaster, but as a new normal, one high tide at a time. To put it simply, the moon's orbit is not changing drastically, our perspective on it is. The 5-degree tilt means that sometimes the moon's gravitational tug on the equator is stronger, sometimes weaker. It's a slow oscillation, more like a breathing pattern than a pendulum. And because the cycle takes almost 19 years, it moves on a timescale that humans rarely feel. Just long enough to forget, just short enough to repeat within a lifetime. The last time the cycle peaked, in 2015, scientists noticed something curious. Flood frequency records along the US Atlantic and Gulf coast jumped sharply, even in the absence of major storms. Streets in Miami, Charleston, and Norfolk flooded during calm weather, simply because high tide alone was enough to breach the drains. Locals called it sunny day flooding, but the cause was written in the sky. The moon had reached the part of its wobble that magnified the tides. Now the same mechanism is returning, but with a difference. The baseline sea level is higher than it was 18 years ago. The next nodal maximum, arriving around the early 2030s, will therefore start from a slightly higher ocean. The gravitational rhythm is the same, but the stage has shifted upward. That's why NASA's projections warn of compounding effects. The nodal cycle doesn't cause sea level rise, it only modulates it, yet its amplification can make the difference between a harmless high tide and a flooded neighbourhood. To visualise the mechanics, think of Earth and Moon as partners in a slow dance. The Earth spins daily while the Moon circles monthly, but overlaid on those quick rhythms is this deeper pulse, the tilt of the Moon's orbit gradually rocking back and forth, controlling how far the lunar pull leans north or south. Every 9 and a bit years, the system passes through its midpoint where the tides are most moderate. 9 years later, it reaches an extreme, when tides are amplified worldwide. It's the longest metronome you've never noticed. The scale of this influence is astonishing when you consider how small the moon is compared to the sun. The sun is vastly more massive, yet because it's so far away, its tidal effect is only about half the moon's. Together, they compose the ocean's endless breathing pattern. And that pattern is written not in chance, but in geometry. The tilt, the distance, the orbital nodes, each measurable, predictable, and beautifully precise. Scientists have traced the nodal cycle backward through centuries of tide data. Mariners of the 19th century kept meticulous records of water levels, and those measurements reveal the same repeating pulse. Ancient coastal structures, harbours, salt pans, fishing terraces, sometimes show wear patterns consistent with the timing of nodal maxima, as if civilizations unconsciously built around this lunar rhythm. Even in myth, you can sense the memory of it. Stories of seas that rise every generation, of moons that grow stronger, of tides that forget their boundaries. Behind every legend was a quiet equation. From a distance, the moon's nodal cycle seems almost too subtle to matter, yet it governs the boundaries of continents. A shift of just a few centimetres in the average high tide can alter where mangroves grow, how estuaries mix salt and fresh water, and how coastal ecosystems survive. It's also a reminder that planetary dynamics aren't just grand, violent events. Sometimes they're gentle patterns that accumulate consequences through patience. If you were to fast-forward Earth's oceans in time-lapse, the nodal cycle would appear as a slow global inhale and exhale of the sea itself. Every 18 years, the oceans lean in slightly closer to the moon, then lean back. Each pulse reshapes coastlines, redistributes sediment, and redefines what we consider the edge of the world. NASA's models for the coming decades show that the next amplification phase will overlap with the natural perigee-apogee cycle, the difference between when the moon is closest or farthest from Earth each month. When those align, the tides can reach their absolute extremes. It's not that the moon suddenly grows more powerful, it's that its geometry lines up perfectly for resonance. The same principle that makes a swing go higher when pushed in rhythm applies here, only the swing is an ocean basin, and the rhythm is cosmic. Some people find this knowledge unsettling, the idea that an invisible wobble in the moon's orbit can flood cities. But there's also something strangely comforting about its predictability. Unlike earthquakes or storms, the lunar nodal cycle is clockwork. It can be mapped centuries in advance. We already know when the next amplification will peak, how long it will last, and when it will fade. The question is simply whether we will be ready when the tide keeps its appointment. The ocean does not hurry, it never forgets. Every wave that reaches the shore is part of a pattern older than life. The moon, tilted just 5 degrees off perfection, ensures that pattern keeps changing, that the sea never grows complacent. If the tides are Earth's heartbeat, then the lunar nodal cycle is its pulse of memory, slow, deliberate, and certain. So when the water begins to rise a little higher in the early 2030s, when high tide feels just a bit less predictable, don't imagine the sea as angry or alive. Imagine it as patient. It's only following instructions written by gravity long before we built our coasts. The waves are not warning us, they're keeping time. Alright, whether you're watching the tide from a harbour wall or looking up at a pale moon through passing clouds, there's a strange comfort in the thought that both the moon and the sun are predictable. They rise, they fall, they repeat. Yet every so often the two bodies fall into a perfect rhythm, and when that happens, the calm predictability of the sea briefly vanishes. The waves, the weather, and the pull of gravity itself begin to stack, and the result can be catastrophic. So what happens when every tide joins forces? To understand that, we need to look at how the moon and sun share the job of moving our oceans. The moon is the main architect of tides, its gravity pulling the water toward it and creating two bulges, one on the near side of the planet and one on the far side. But the sun, although far more massive, is about 400 times farther away, and its gravitational influence on our tides is only about half as strong. Normally these two forces work slightly out of sync, but sometimes they align perfectly. When the moon and the sun line up on the same side of Earth, their pulls combine. This produces what scientists call spring tides, not named for the season, but from the Old English word springan, meaning to rise. These are the highest high tides and the lowest low tides, the extremes of the ocean's breadth. Roughly twice a month during new and full moons, This gravitational duet amplifies the normal rhythm of the sea. Conversely, when the moon is at a right angle to the sun relative to Earth, their pulls partially cancel each other out, creating neap tides, gentler and more moderate. On any given coastline, these shifts are familiar. Fishermen, sailors, and coastal dwellers have read the moon's phases for thousands of years, understanding instinctively when the tides will rise and fall. But there's another layer of rhythm, a deeper, slower harmony, when the moon's 18.5-year nodal cycle aligns with the sun's influence. When that happens, every factor that controls the tides, the moon's tilt, its distance from Earth, its position relative to the sun, can synchronize, producing tides of extraordinary strength. It's like a resonance, the same principle that can make a glass shatter when a note matches its frequency. Except here, the note is gravity, and the glass is every ocean basin on Earth. When this resonance peaks, we see not just higher tides, but a world where coastal flood maps start to redraw themselves. The last time this happened was around the year 2015, when the lunar nodal maximum coincided with strong solar alignment events. That autumn, both the United Kingdom and the United States issued major flood warnings, particularly in September when the full moon's alignment with the sun produced extremely high spring tides. In Britain, the results were subtle at first: overflowing estuaries, unusually high river surges, a few submerged coastal roads. But when that pattern merged with heavy rainfall and winter storms a few months later, the outcome became devastating. In December 2015, Storm Desmond struck northern Britain, bringing record-breaking rainfall that fell onto already swollen rivers. The result was a chain of catastrophic floods. Cumbria, Lancashire, and parts of Scotland saw water levels higher than anything recorded in a century. The economic damages were estimated at over £1 billion. In the United States, similar interactions occurred in the Carolinas, where late-season floods combined with tidal amplification to devastate communities from Charleston to Columbia. The link between the skies and the floodwater below was not mystical, just mechanical, but no less awe-inspiring for that. When the lunar nodal maximum returns in the early 2030s, it will again align with periods of strong solar influence, creating an almost perfect resonance between the moon, the sun, and the Earth's oceans, NASA's sea level change. Science team predicts that this upcoming convergence could multiply coastal flooding frequency by a factor of 3 or 4 in many regions. And because baseline sea levels have already risen since the last nodal cycle, the consequences could be far greater. To visualize this, imagine the ocean as an enormous bowl of water sitting on a slowly moving table. The moon's gravity nudges the water from side to side, while the sun's gravity rocks it in a different direction. Most of the time, these motions interfere with each other, a chaotic balance that keeps the tides within their ordinary limits. But occasionally the wobbles line up. The table tips in both directions at once, and the water rushes toward one edge, spilling over. This resonance doesn't happen everywhere at once, nor does it arrive as a single cataclysmic event. Instead, it manifests through local amplifications. One city's harbour sees record-high tides, another's storm drains back up, another's barrier wall just barely overtops. Coastal scientists sometimes describe it as the stacking of anomalies, when multiple natural cycles overlap and push the system beyond its usual equilibrium. It's not superstition, it's physics. The lunar nodal cycle affects the amplitude of the tides. The Earth's orbit and the Sun's gravitational alignment determine their timing. Add atmospheric pressure patterns, local wind stress and rainfall, and you get the recipe for either calm seas or calamity. Each factor alone might be harmless, but when all of them align, as they did in 2015, and likely will again around 2033, the results can be spectacularly destructive. Scientists can now simulate these alignments with remarkable precision. Satellite data, tide gauges, and climate models allow researchers to predict when the moon's orbit will amplify the tides, when solar gravity will reinforce that effect, and when seasonal patterns could make matters worse. The irony is that our ancestors without computers already understood this intuitively. Ancient navigators tracked flood patterns across decades, timing major constructions like harbours and temples to lunar cycles. The British Isles' earliest coastal maps even show notations around years of great tides, almost certainly nodal maxima witnessed by people who didn't know the word for them, but recognised the rhythm. When the sun and moon pull together, even the shape of the coastline matters. Long, shallow estuaries, like those found along the Thames, the Bay of Fundy, or the Gulf of Mexico, act as amplifiers, funneling the incoming tide into narrow spaces where it piles higher and higher. During a nodal maximum, these regions experience some of the highest spring tides on the planet. In contrast, steep, rocky coastlines disperse the energy more easily, absorbing the impact like a jagged breakwater. The energy involved in these tidal resonances is difficult to imagine. The total mass of water moving during an ordinary high tide is equivalent to billions of Olympic-sized swimming pools. When the moon and sun synchronize, that movement becomes more focused and forceful, transferring enormous amounts of kinetic energy into the coastlines. That's why tides can carve channels, move sediment, and even influence the stability of delta regions. But despite the scale of the phenomenon, its beauty remains hypnotic. If you've ever stood on a beach during a full moon and watched the water climb higher than you remember, you've witnessed part of that cosmic choreography. There's something eerie about the precision of it. Two distant spheres, their gravitational pulls weaving together over unimaginable distances, yet perfectly timed to a rhythm that dictates where every coastline begins and ends. NASA's models warn that when this alignment returns in the 2030s, it will coincide with warmer global temperatures and higher mean sea levels, factors we'll explore later. The combined effect could see low-lying regions such as the Gulf Coast, the Pacific Islands, and Southeast Asia experiencing chronic flooding, where tides intrude far more often than infrastructure was built to handle. The science is clear. These are not sudden disasters, but the outcome of overlapping cycles we can measure and predict. And yet, there's something humbling about realizing that every modern flood defense, every concrete seawall and tidal gate is ultimately playing against a clock wound by celestial mechanics. Humanity builds, the moon tilts, and gravity waits. The Earth's relationship with its moon and sun is the quiet choreography of physics played out in water. Each wave is a whisper of that dance, each flood a reminder that stability is only ever temporary. Perhaps the strangest part is how predictable it all is. We can name the year and the month when these alignments will peak, and still, the outcome depends on how prepared we are when the tides arrive. So, the next time you see a full moon rising over the sea and the horizon seems just a little closer to your feet, remember, you're watching a planetary duet, a gravitational harmony older than the continents themselves. The moon pulls, the sun steadies, and the oceans answer. It is not vengeance or warning, only resonance, the universe keeping time in water. Imagine if trees could do civil engineering, not metaphorically, literally reshape coastlines, slow waves, trap sediment, and build land faster than storms can wash it away. In many places they already do. While humanity debates seawalls and surge barriers, a quieter force has been protecting shores for millions of years, the mangrove. The joke among coastal ecologists is that these trees work overtime without asking for funding. They just need salt water, sunlight, and time. But the real question is, can nature out-engineer us at flood control? Mangroves are among the strangest forests on Earth. They grow where few plants dare, in brackish coastal zones that flood twice a day and choke with salt. Their roots arch and twist above the mud like the ribs of some living cathedral, filtering salt and anchoring soil that would otherwise drift away. Beneath the surface, their roots knit into dense lattices that trap sediment with every tide. Over decades, these systems literally build land centimetre by centimetre, tide by tide, turning bare coastlines into stable marshes. Each mangrove tree is a quiet hydraulic engineer. Its aerial roots dissipate wave energy by friction. When water flows through a mangrove forest, the chaos of incoming waves is converted into slow swirling eddies, reducing their force by as much as 2/3 before they reach the shore. Researchers have found that 100 metres of healthy mangrove forest can cut the height of incoming waves in half. The physics behind it is simple and elegant. Drag. Water flows around thousands of small roots, losing energy in the process. It's the same principle that engineers use when designing energy-dissipating structures in harbours, except mangroves invented it first. And unlike concrete, Mangroves grow stronger with time. Their trunks thicken, their roots extend, their leaf litter becomes soil. Over years, a mature mangrove forest can raise its own floor level by trapping sediment, countering sea level rise naturally. It's a living feedback system, a design any human engineer would envy. Mangroves don't just manage waves, they also handle carbon, and in this, they outperform even the densest rainforests. Scientists call them blue carbon ecosystems, meaning coastal environments that lock carbon into sediment rather than releasing it. Because their roots grow in oxygen-poor mud, the organic matter that falls from them, leaves, bark, roots, decomposes slowly, trapping carbon for centuries. Per square metre, mangrove forests can store up to 4 times more carbon than tropical rainforests of the same size. In the global carbon budget, that makes them invaluable. Restoring mangroves in coastal regions isn't just about flood prevention. It's one of the most efficient climate mitigation strategies we have. A hectare of mangroves can absorb roughly 1,000 tonnes of carbon dioxide over its lifetime, while continuing to provide storm protection and fish nursery habitat for free. That's a rare combination of ecological function and economic value. But despite their brilliance, mangroves are disappearing. Around a third of the world's mangrove cover has been lost in the last century, cleared for shrimp farming, coastal development and tourism. The irony is bitter. In trying to expand human space along the coasts, we often remove the very systems that make those coasts livable. Without mangroves, tidal surges hit harder, erosion accelerates, and salt water intrudes into freshwater aquifers. It's not poetic justice, just feedback. Some countries have begun to understand this, especially where water management is a matter of survival. Nowhere illustrates this better than the Netherlands, a nation that has spent centuries negotiating with the sea. Roughly 1/3 of Dutch territory lies below sea level, and another third sits just above it. For centuries, the Dutch built barriers, levees and drainage canals to hold back water. But in recent decades, they've begun to ask a new question. Instead of fighting water, can we live with it? That question reshaped Dutch engineering philosophy. The modern approach is known as building with nature. It blends ecological and structural design, restoring natural systems like dunes, wetlands and estuaries to work alongside human-built defences. A prime example is the Room for the River project, a nationwide effort to give rivers space to flood safely instead of confining them with higher walls. Engineers lowered floodplains, moved levees inland, and restored wetlands to absorb excess water naturally. It's not just functional, it's elegant. Then there are the polders, perhaps the most famous Dutch innovation. A polder is land reclaimed from the sea or a lake, surrounded by dikes and managed by pumps and canals. Early versions relied on windmills. Today, they're run by advanced automated systems that monitor water levels in real time. But even here, the Netherlands is shifting strategy. Modern polders are being designed to flood intentionally when needed, to act as controlled buffers rather than vulnerable territories. It's a philosophical shift as much as a technical one, understanding that water is not the enemy, but a partner in design. In recent years, Dutch engineers have begun exporting these lessons abroad, to delta regions like Bangladesh, Vietnam and Indonesia, where urbanization collides with rising seas. And increasingly, they're blending infrastructure with biology. The idea is simple: let nature do part of the work. In Jakarta, hybrid projects are combining mangrove restoration with seawall reinforcement, allowing living roots to absorb wave energy before the waves reach the wall. In the Mississippi Delta, engineers are reintroducing sediment flows from the river to rebuild coastal marshes. The goal isn't to conquer nature, but to collaborate with it. Mangroves, salt marshes, coral reefs, they all perform ecosystem services that concrete can't replicate easily. Yet, we can design infrastructure that mimics their physics. Breakwaters shaped like branching roots or honeycomb reefs can disperse wave energy in similar ways. Floating urban wetlands are being trialled in Singapore and Rotterdam, merging plant life with buoyant architecture to create living barriers that adapt and grow. The line between ecology and engineering is beginning to blur, and that might be our best hope in a wetter future. This shift toward cooperative design carries philosophical weight too. For most of history, humanity has seen itself as separate from nature, building against it, shielding from it, draining it, cutting it back. But the more we learn about systems like mangroves, the clearer it becomes that resilience comes from participation, not opposition. A seawall resists until it fails. A forest bends and reforms endlessly. There's a kind of humility in letting trees handle part of your flood control strategy. The math supports it. In some regions, every dollar spent on mangrove restoration yields up to $15 in avoided flood damage. Their roots are low-tech but high efficiency, evolving over millions of years of trial and error, a longer research phase than any engineering firm could afford. The lesson from the Netherlands and from the mangrove swamps of the tropics is the same. Stability doesn't mean stillness. It means flexibility, adjustment, co-evolution. In this way, mangroves and machines aren't opposites. They're stages of the same story. Both are methods of managing uncertainty, one biological, one mechanical, and both are teaching us that the future of flood control may lie not in domination, but in dialogue. Perhaps the greatest irony is that nature never needed blueprints. The design was always there, growing in the intertidal mud, waiting for us to notice. The roots curve to slow the water, the trunks rise to breathe air when flooded, the leaves filter salt. Every problem is solved by growth, not resistance. It's the kind of quiet genius we could stand to learn from. So yes, maybe the best engineers aren't us. Maybe they're the trees standing knee-deep in brine, filtering salt through their veins and holding the line between sea and land. They ask for no maintenance contracts, no policy paper, no budget approval. Just room to grow and a little patience. In the end, we might realize that the future of coastal survival depends not on whether humans can outbuild the ocean, but whether we can rejoin the conversation with it. The sea moves, the trees hold, the cities adapt, and for once, everyone is working with the same tide. All right. Somewhere above the thin blue veil of our atmosphere, space is quietly raining down particles. They come from beyond the solar system, beyond even our galaxy, fragments of exploded stars travelling near the speed of light. When they strike the upper air, they fragment again, creating cascades of subatomic debris that fall invisibly toward the Earth. These are cosmic rays, not rays at all but charged particles, and they may be shaping the weather in ways we're only beginning to understand. So, can storms in space make clouds on Earth? Every second, thousands of cosmic particles hit every square metre of our planet. Most of them are protons or atomic nuclei born in supernovae, hurled outward across the universe until they reach our solar system. Normally, the sun's magnetic field, stretched across space by the solar wind, deflects much of this radiation, forming a vast protective bubble called the heliosphere. When the sun is active, its field is stronger, and fewer cosmic rays make it through. When the sun is quiet, that field weakens, allowing more to slip past. This simple relationship, solar activity up, cosmic rays down, solar activity down, cosmic rays up, has been measured for over a century. But the possible consequences of that fluctuation may extend beyond the vacuum of space. Some scientists suspect that these invisible visitors may influence Earth's cloud formation, subtly shaping our weather and even long-term climate cycles. Here's the basic idea. Clouds form when water vapour condenses around tiny particles in the atmosphere called aerosols, microscopic seeds like dust, pollen, sea salt, or industrial pollutants. These act as cloud condensation nuclei. The more nuclei there are, the more places water can gather and condense into droplets. Now imagine that every cosmic ray entering the atmosphere creates a tiny ionization trail, a path of charged particles. These ions could, in theory, act as additional condensation sites, helping water molecules stick together and form droplets where they otherwise wouldn't. This concept, called ion-mediated nucleation, has fascinated researchers for decades. The first to connect cosmic rays and clouds was the British scientist Edward Ney in the 1950s, and the idea was later expanded by Henrik Svensmark in the 1990s. Svensmark's hypothesis proposed that when the sun's magnetic field weakens, during solar minima, more cosmic rays enter Earth's atmosphere, increasing low cloud cover. Those low clouds reflect more sunlight, cooling the planet slightly. Conversely, when the sun is active and cosmic rays are deflected, fewer clouds form, allowing more sunlight to reach the surface and warming it. If true, this mechanism would make the sun's 11-year cycle not just a solar phenomenon, but a subtle climate rhythm, affecting temperature and precipitation on Earth. It would mean that even distant supernovae, by adding a few % more cosmic radiation to our skies, could alter the planet's cloudiness. The universe, in other words, might occasionally participate in our weather report. The problem is that proving this link has been extraordinarily difficult. Clouds are messy, chaotic systems influenced by temperature, humidity, aerosols, and circulation patterns. Separating the signal of cosmic rays from all that noise is like trying to hear a single violin in a thunderstorm. Some studies have found faint correlations between cosmic ray flux and global cloud cover. Others have found none. The evidence swings back and forth with the same rhythm as the solar cycle itself. To bring clarity, physicists decided to recreate the process under controlled conditions. At CERN, the European Organisation for Nuclear Research, scientists launched an experiment called CLOUD, cosmics leaving outdoor droplets. It's exactly what it sounds like. A giant, precisely sealed chamber where researchers can inject trace gases, control humidity, and simulate cosmic rays using particle beams. The idea was to see whether increased ionization really does trigger the formation of cloud droplets. The results were intriguing but nuanced. Yes, cosmic rays can enhance the formation of certain types of aerosols, especially when vapours of sulfuric acid and ammonia are present. But whether those extra particles actually grow large enough to become full-fledged cloud droplets is less certain. In most atmospheric conditions, the effect appears modest, perhaps a few % change in particle numbers. Still, even small changes integrated over global scales and long times might matter. The beauty of science lies in its humility, the willingness to admit maybe the cosmic ray hypothesis hasn't been proven or disproven, only refined. What's clearer now is that solar activity and cloud covers do show some synchrony, particularly at high latitudes, where cosmic ray flux is strongest. During extended solar minima, such as the Maunder minimum of the 17th century, sunspots nearly vanished for decades, and Europe experienced the Little Ice Age with colder winters and advancing glaciers. Coincidence, perhaps, but the timing continues to intrigue climatologists. To trace this relationship deeper in time, scientists have turned to ice cores and tree rings. When cosmic rays strike the atmosphere, they create isotopes like beryllium-10 and carbon-14, which fall to Earth and become locked in snow and wood. By measuring their concentrations in ancient samples, researchers can reconstruct how cosmic radiation has varied over thousands of years. These isotope records show a remarkably consistent pattern. When solar activity wanes, cosmic rays rise, and when cosmic rays rise, temperatures on Earth often dip, if only slightly. It's a delicate dance. The temperature shifts linked to solar minima are usually less than half a degree Celsius, hardly apocalyptic but noticeable in long climate records, enough to influence regional weather patterns, crop yields, or glacial expansion. In essence, cosmic rays may provide the faint metronome beneath Earth's climate variability, a background rhythm of deep space physics beating beneath our atmosphere. There's something poetic about the idea. Exploding stars light years away, sending particles that eventually help sculpt the clouds that water our fields. The same processes that forge heavy elements in supernovae may also, indirectly, decide whether a farmer sees rain. It's a story that connects the farthest reaches of space to the soil under our feet. Of course, not everyone agrees that cosmic rays play more than a supporting role. Many atmospheric scientists argue that terrestrial factors, volcanoes, ocean currents, greenhouse gases, explain the observed patterns without invoking extragalactic input. And they may be right. But the search continues because even small secondary effects matter when modelling climate over millennia. Every layer of causation brings us closer to understanding the full orchestra behind our planet's weather. The question remains open. How much do cosmic rays really influence our clouds? The data suggests there's an effect, but not a dominant one. More like a faint harmony beneath louder instruments. During solar maxima, the sun's magnetic field shields us better, and cosmic ray counts drop. During solar minima, the shield thins, and our atmosphere receives more high-energy particles. Perhaps that extra ionization just nudges the balance. A few more cloud seeds here, a few less there. Subtle, cumulative, but real. In the end, what this teaches us is that Earth's climate is not an isolated system. It's a dialogue between the sun, the atmosphere, and the galaxy beyond. Cosmic rays remind us that even the void is not empty. It hums with energy and consequence. Every time you see a cloud drift across the sky, you might be watching the end of a chain reaction that began in a star that died before our species even existed. So, can storms in space make clouds on Earth? The honest answer is, perhaps. The evidence flickers like the aurora itself, bright, fleeting, and worth watching. Because even if the connection proves small, it speaks to a larger truth, that our world, our weather, and our very breath are part of a system much older and larger than we can see. Somewhere in the branches, a blue tit adjusts a twig in its nest, unaware that its small act of timing has been written, in part, by the sun. We tend to imagine that the solar cycle only matters to astronomers, but countless species are quietly listening to it in ways we can't. While humans need telescopes and satellites to measure the sun's moods, other creatures seem to feel them directly, through light, magnetism, and the subtlest cues in the atmosphere. How do they sense solar moods we can't see? When scientists first began studying solar influence on animal behaviour, they expected the results to be simple. Maybe birds just react to temperature or daylight. But the patterns turned out to be too consistent, too strange. In the early 2000s, a long-term study of blue tits in the Netherlands found that their nesting schedules shifted in step with the number of sunspots on the sun's surface. In years of high solar activity, when the sun's magnetic field is strong and flares erupt more often, the birds laid their eggs earlier. In years of solar quiet, they delayed. The researchers checked every possible explanation: local weather, temperature, food availability, and still the correlation held. Somehow the sun's rhythm was being heard in the forest. The question is, how? Birds, after all, aren't physicists. They don't see plasma storms. Yet, they live inside the magnetic field those storms shape. Every 11 years, as the sun's polarity flips, the magnetic conditions surrounding the Earth subtly change. Cosmic rays that would otherwise reach the planet's surface are deflected more or less strongly, depending on how turbulent the solar wind is. That variation affects ionization in the upper atmosphere, and, possibly, the Earth's own magnetic field lines, the invisible routes many migratory birds follow. For a pigeon or a robin, magnetic sense is not a metaphor, it's a biological compass. Deep within the eyes of many birds lies a pigment called cryptochrome, sensitive to blue light and magnetism at the same time. When exposed to certain wavelengths, it produces paired electrons whose spins can be influenced by Earth's magnetic field. To the bird, this becomes a faint visual pattern, a kind of ghostly overlay that shows direction. It's as if the magnetic field itself appears as a dim haze across its field of vision. Now imagine what happens when solar storms or sunspot peaks distort that field. For us, the effect is invisible. For a bird, it's as though the world's compass briefly flickers. Migratory routes bend slightly. Pigeons that normally navigate home with precision might find themselves wandering miles off course during periods of intense solar activity. Researchers have even noticed that homing pigeons released during geomagnetic storms take longer to return, flying in hesitant looping paths. When the sun quiets again, their accuracy returns. In one experiment conducted over several decades in the United Kingdom, pigeon racing records were compared with solar data. The results were striking. The greatest navigational errors occurred during solar maxima, when coronal mass ejections and magnetic storms were most frequent. The same pattern appeared in satellite tracking of migratory species. Birds didn't just get lost randomly. They lost direction when the sun was restless. And yet, it isn't only navigation that shifts. Timing, the quiet metronome of reproduction and feeding, seems to follow the solar cycle too. The blue tits in the Netherlands, for example, laid eggs earlier in years when solar activity increased, even when local spring temperatures didn't. The scientists speculated that the connection might come through subtle climatic feedbacks, such as small shifts in ultraviolet radiation or atmospheric transparency. Solar variability can change the distribution of ozone high above Earth, which in turn alters the light spectrum reaching the ground. To a bird's eyes, evolved to sense polarization and narrow colour ranges, that difference might act as a cue. Time to begin. What's fascinating is that no single species seems consciously aware of this influence. It's not intuition or intelligence, it's physics filtering through biology. For migratory birds, the sun is both the clock and the compass. They navigate partly by the position of the sun, compensating for its daily movement using an internal circadian rhythm. When that solar rhythm becomes unpredictable, when sunspot activity alters magnetic conditions, their systems drift, like a clock running slightly fast or slow. Over thousands of generations, evolution may have tuned them not just to Earth's seasons, but to the quiet heartbeat of the sun itself. Pigeons, of course, are the more famous navigators, having served humans for communication long before radio waves existed. Their reliability made them ideal natural instruments to study magnetism. During the Cold War, for instance, some of the earliest research into geomagnetic sensitivity used military messenger pigeons. Scientists noticed that birds released during solar flares often failed to return on schedule. It wasn't sabotage, it was astrophysics. The very plasma bursts we see as beauty in the aurora were, for these creatures, moments of magnetic noise. And it's not only birds. Bees, salmon, sea turtles, even some bacteria use magnetoreception to orient themselves. But birds are special because their behaviour can be directly observed and measured across solar cycles, revealing correlations that connect individual nests to cosmic phenomena. It's an astonishing bridge of scale, from a feathered creature weighing a few grams to the 11-year pulse of a star 150 million kilometres away. The deeper scientists look, the more they find traces of this solar whisper in other patterns of wildlife. Insects that migrate using polarised light appear to shift routes subtly depending on the sun's magnetic mood. Some plankton species at the ocean's surface show growth rate variations linked to solar radiation intensity. It's as if life, in all its forms, carries a memory of where it came from, tuned, even faintly, to the star that made it possible. Of course, not every claim holds up. Some early 20th century sunspot zoologists thought every population boom and bust, from locusts to lemmings, could be explained by solar cycles. The data didn't bear that out. Life is too complex to be ruled by one clock. Yet modern research suggests that small but real effects persist, detectable only over long time scales and large sample sizes. The sun is not puppeteering behaviour, but it may be quietly nudging it, enough to be felt in timing, orientation, or subtle shifts in migration success. Today, as satellites record the sun's every flicker, scientists are refining these connections with precision instruments rather than anecdotes. Sensitive magnetometers placed along bird migratory routes can now correlate navigational deviations with measured geomagnetic fluctuations. Radiotelemetry allows researchers to watch entire flocks respond to space weather in real time. It's science catching up with what the pigeons already knew. If there's a lesson here, it's humility. We live on a planet bathed in the sun's constant light, yet we notice so little of its variability. Birds and other animals don't have that luxury. They are immersed in it. For them, sunlight isn't just illumination, it's information. They read its direction, its spectrum, its interference with magnetism, and they build their lives around those cues. The sun's pulse is written in the timing of eggs, the angle of migration, the invisible trails across a continent's sky. And maybe that's the wonder of it, that a star's changing breath can ripple down through space and manifest as a songbird's decision of when to begin the next generation. While we build observatories to measure solar flares, there are already billions of biological instruments scattered across the planet, recording those changes in behaviour. They are quieter than our sensors, but no less accurate. So the next time you see a bird tracing an invisible path across the sky, or building a nest just as spring begins to stir, it might be listening to something beyond the season, a rhythm older than weather, deeper than instinct. The sun is not only our light but our unseen conductor, setting tempo for creatures that have never stopped watching it. Your pulse right now, that quiet beat inside your chest, may not be as self-contained as you think. For decades, researchers have asked a strange question. Could human biology be faintly synchronized with the sun? not in the mystical sense, but literally through radiation and magnetism. It sounds poetic, maybe even superstitious, until you realise that every heartbeat is an electrical signal, and every electrical signal is, at least in theory, something the sun could touch. So could your pulse be following an 11-year rhythm too? The idea first began flickering in medical journals in the late 20th century, when epidemiologists noticed odd correlations between the solar cycle and certain physiological patterns. Heart rate variability, blood pressure, even hospital admissions for cardiovascular issues seemed to rise and fall in faint sync with sunspot numbers. Around the 1980s, Soviet and European researchers began comparing medical data against solar indices, and the results were perplexing enough to merit further study. Some teams found that during solar maxima, when the sun's magnetic activity peaks and geomagnetic disturbances ripple through Earth's field, there was a small but measurable uptick in heart attacks and strokes. During solar minima, rates appeared to dip slightly. Other studies noted fluctuations in blood viscosity, melatonin levels, and even reaction time, as if the human body was subtly adjusting to the electromagnetic weather. The effects were tiny, nowhere near enough to explain individual outcomes, but statistically consistent across large populations. One early hypothesis was that geomagnetic storms, those same disturbances that make the auroras dance, could influence the autonomic nervous system, the unconscious circuitry that controls heart rate and blood vessel constriction. The theory was not far-fetched. Human biology is electrochemical. Our cells rely on tiny voltage gradients to communicate. Magnetic fields, even weak ones, can in principle nudge those signals slightly. The question was how much, and whether the sun's field could possibly reach that deep. The most cited early work came from researchers in Russia, Canada, and Japan who compared long-term medical data sets to the 11-year solar rhythm. They reported that blood pressure and heart rate variability tended to dip during geomagnetic quiet and rise during geomagnetic turbulence. Some speculated that melatonin, the hormone regulating circadian rhythm, could act as a mediator, since its production in the pineal gland is light-sensitive and possibly affected by geomagnetic changes. When solar storms disturbed the field, melatonin levels sometimes dropped, subtly altering sleep cycles and mood regulation. Of course, whenever correlations appear between space weather and human health, skepticism follows close behind, and rightly so. The effect sizes were small, and biological systems are noisy. Many of these studies relied on aggregate data, making it impossible to separate causation from coincidence. But even cautious scientists agreed that there might be some form of bioelectromagnetic sensitivity worth investigating. In the 1990s and early 2000s, more sophisticated instruments arrived. With better satellite data and ground magnetometers, researchers could track the K-index, a measure of geomagnetic activity, and compare it directly to physiological metrics. Some experiments placed volunteers in magnetically shielded chambers to simulate the calm of a solar minimum, while others exposed subjects to low-level magnetic fluctuations. Changes in blood pressure, heart rate, and brainwave coherence were occasionally observed, though often inconsistently. By the 2010s, the field had matured into what some called heliobiology, the study of solar-terrestrial interactions with living systems. It remained fringe but increasingly data-driven. One of the more rigorous analyses, published in Environmental Health Perspectives, found modest statistical links between geomagnetic storms and cardiovascular mortality. The authors proposed that magnetospheric disturbances could subtly alter geomagnetically induced currents, tiny electric fields generated on Earth's surface during storms, which in turn might influence cardiac electrophysiology in sensitive individuals. Again, the effect was minute. Nobody was getting a heart attack because of a solar flare, but the signal was there, faint and rhythmic. Meanwhile, psychological studies noticed something equally strange. Shifts in mood and behaviour seemed to track the solar cycle too. In some populations, rates of depression and anxiety showed mild correlation with solar minima, while manic symptoms occasionally increased near solar maxima. It was hardly a universal pattern. Culture, latitude, and environment mattered far more. But the idea that our collective mood might be slightly solar-powered became an irresistible headline. Maybe that's why we call it a sunny disposition, one researcher joked dryly in a conference paper. Still, The connection between radiation and psychology remains speculative. Some propose that changes in cosmic ray flux, higher during solar minima when the sun's magnetic shield weakens, might affect serotonin or dopamine levels indirectly by influencing atmospheric ionization or oxidative stress. Others argued that these effects were too small to matter biologically. The truth likely sits somewhere in the middle. The sun probably can nudge us, but only gently, through complex pathways we barely understand. A few scientists turned the question upside down. If we're affected by the sun, could our own internal rhythms reflect it? Studies of circadian cycles, those 24-hour oscillations in hormone levels, temperature, and alertness, suggest that some individuals exhibit ultradian and infradian patterns as well, spanning days, weeks, or even years. In theory, if a biological clock were sensitive to long-term electromagnetic variation, an 11-year modulation might not be impossible. So far, though, evidence for such deep cycles in humans remains inconclusive. What's undeniable is that other species show stronger links. Migratory animals, as we saw, respond to magnetic fields directly. Plant growth cycles can shift subtly with solar radiation. Even bacterial growth rates in laboratory cultures have shown variations correlated with geomagnetic activity, though the mechanism remains a mystery. We may simply be less tuned, less dependent on those external cues, insulated by technology and artificial light. The sun's rhythm still plays, we just don't always hear it. One of the more pragmatic areas of solar biology research concerns space medicine. Astronauts beyond Earth's magnetic shield face direct exposure to solar and cosmic radiation. Their physiology offers a real-time experiment in how solar activity interacts with living tissue. Radiation bursts during solar storms can damage DNA and increase cancer risk, while chronic exposure can affect the cardiovascular and nervous systems. Monitoring solar cycles has therefore become essential to mission planning. What began as a speculative field now has practical stakes. Because outside our magnetic cocoon, the sun's influence is no longer subtle. For those of us on the ground, the picture is more reassuring. Earth's magnetosphere and atmosphere shield us from most radiation, so whatever biological signal the solar cycle leaves in our bodies is likely faint, layered beneath stronger terrestrial influences: diet, stress, pollution, genetics. The sun may set the stage, but life writes its own script. Still, it's hard to resist the poetry of it. A star 150 million kilometers away, pulsing every 11 years, possibly stirring slight echoes in our hearts, our hormones, maybe even our collective mood. It's a hypothesis too fragile to claim, too persistent to dismiss. The universe has a way of leaving fingerprints where we least expect them. If there is a lesson in these studies, it's the humility of thresholds, the point where detection meets imagination. We can measure the sun's flares in precise watts and Tesla, but we can't yet map their quiet ripples through our biology. Perhaps they exist only as faint harmonies, the kind that fade when we look too closely. Or perhaps one day, with better data and better patience, we'll find that our species carries a rhythm not entirely its own, an echo of the star that made life possible in the first place. Until then, the idea of being solar-powered remains a charming metaphor. But maybe, somewhere deep in the statistics, there's a literal truth flickering. 1 heartbeat per 11 years. What if creativity didn't just happen inside our skulls but was coaxed into existence by a restless star? 80,000 years ago, long before cities, language or myth, Earth's skies pulsed under a sun that flared brighter and stranger than today. Some researchers think the timing might not be coincidence, that bursts of cosmic radiation and the quiet violence of solar storms may have nudged our ancestors' brains toward new kinds of chaos, the kind that can imagine. It's a bold hypothesis that cosmic weather may have played a role in the evolution of thought itself. Thank your local star for abstract art, perhaps. The idea is not that radiation made humans intelligent overnight, but that environmental noise, cosmic rays, magnetic field fluctuations, background ionization, could have subtly reshaped how early neural systems handled information. Brains are, in a sense, electrical storms contained in bone. Every thought is a cascade of ions moving across membranes, every spark of imagination a carefully organised burst of chemical electricity. In that sense, solar radiation is our cosmic cousin. Both rely on charged particles moving through magnetic fields, one inside neurons, the other across space. Now imagine Earth during a period of solar hyperactivity. More flares, stronger geomagnetic disturbances, and a thinner protective field during one of the planet's temporary magnetic weakenings. Radiation doses wouldn't have been catastrophic, but the background flux could have increased slightly, altering mutation rates, influencing melatonin cycles, or even changing the atmospheric chemistry that governs how much light reached the ground. The effects on ecosystems, circadian rhythms, and human biochemistry could have been small but compounding, enough to shift the tempo of evolution's improvisation. Some anthropologists have noticed curious coincidences. Around 70 to 50,000 years ago, genetic and archaeological evidence suggests an acceleration in symbolic behaviour, more complex tools, ornaments, pigments, carvings. That doesn't mean the sun did it, of course. Climate instability, demographic pressure, and social learning all played massive roles. But during that same window, the planet's magnetic field was weaker than average, and cosmic ray influx higher. Could it be that, occasionally, the universe adds static to the evolutionary channel, noise that helps the system find new solutions? It's worth remembering that mutation itself, the raw fuel of evolution, depends on randomness. Radiation, from cosmic rays to ultraviolet sunlight, is a constant background source of genetic variation. Most of those mutations are neutral or harmful, but a few can alter neural architecture in ways that, under pressure, prove advantageous. Evolution doesn't plan. It in neuroscience adds another intriguing layer. Human creativity, at least as we understand it, often arises from a balance between order and disorder, between structured networks like the prefrontal cortex and more chaotic associative regions like the temporal lobes. Too much order, and thought becomes rigid. Too much chaos, and it becomes incoherent. What if external electromagnetic conditions occasionally tipped that balance? Not by inspiring ideas, but by slightly changing how neurons synchronize, how rhythms in the brain's electrical activity align. Some studies on geomagnetic variation show subtle effects on brainwave coherence, especially in alpha and theta frequencies, the ones linked to relaxed focus, imagination, and abstract thinking. Now stretch that idea over evolutionary time. A species living for hundreds of thousands of years inside a slowly oscillating electromagnetic environment might develop resilience to noise, or perhaps learn to use it. Brains that could maintain function amid fluctuating fields might also become better at generating flexible, non-linear patterns of thought. In other words, the capacity for creativity could be a byproduct of coping with cosmic interference. It's the kind of idea that sits somewhere between neuroscience and science fiction, but it's grounded in a real principle. Life evolves to survive variability. When the environment is stable, efficiency wins. When it's unpredictable, adaptability and experimentation win. And there are few things more unpredictable than the sun experiments endlessly. A little extra energy from the cosmos might have sped up the sampling rate. We can even test this reasoning in the fossil record, though only indirectly. Isotopic evidence shows that cosmic ray exposure on Earth's surface fluctuates with solar and geomagnetic cycles. In periods of weaker magnetism, more high-energy particles reach the atmosphere, increasing the production of isotopes like beryllium-10 and carbon-14. These align with small climatic variations, but perhaps also, indirectly, with biological ones. Higher radiation means slightly faster mutation rates in everything from bacteria to mammals. Over many generations, that extra noise could seed diversity in neural development pathways, giving rise to brains wired just differently enough to imagine fire, language, or gods. There's another angle: cosmic radiation's effect on serotonin and dopamine systems. Modern experiments show that changes in background ionization can alter the activity of neurotransmitters related to mood, curiosity, and risk-taking. If similar mechanisms existed in early hominins, environmental radiation could have shifted behavior in subtle ways, making some individuals more exploratory, more prone to novelty-seeking. Over time, those tendencies could spread if they offered survival advantages, say, through innovation or migration. Creativity, in that light, might be what happens when biology metabolizes uncertainty. We shouldn't overstate it. Correlation is not causation, and the data from deep prehistory are far too sparse for firm conclusions. But it's not implausible that cosmic variability played a small but persistent background role in shaping the tempo of human evolution. Our species is, after all, a product of radiation. Sunlight drives the ecosystems that feed us, ultraviolet light forges the vitamin D our bodies require, cosmic rays sculpt our atmosphere, and mutation itself, the very machinery of evolution, depends on the random impact of energetic particles. Without radiation, there would be no variation. Without variation, no evolution. So perhaps it's not so strange to wonder if, from time to time, those cosmic dice rolls produced neural architectures capable of abstraction. Perhaps what we call genius is just the stable side effect of an organism forged in radiation's quiet storm. In the laboratory, creativity looks messy. Flashes of divergent thinking followed by convergence, moments of disorganization resolved into pattern. In cosmic terms, it's the same story. The sun flares chaotically, then stabilizes. Magnetic lines twist and untwist, releasing energy that lights the aurora. Maybe our neurons learn that dance by watching. Some astrophysicists point out that the timing of solar activity might have intersected with crucial moments in our species' migrations. Stronger solar radiation increases cosmic ray ionization in the atmosphere, which can affect cloud cover and climate. Those small shifts could have changed rainfall patterns, vegetation, and animal movements, indirectly shaping human exploration routes. A slightly wetter valley, a slightly cooler refuge, enough to influence where people settled, where they met, where they traded. Out of those new encounters could have come innovation, language exchange, and art. So maybe the real creativity isn't in the neuron but in the network, between species, between climate zones, between worlds. Solar activity could have altered not just minds but the conditions minds lived within, setting off chains of feedback that eventually led to symbolic thought. The cosmos doesn't have to sculpt brains directly if it can rearrange the world they adapt to. The deeper we look, the more porous the boundary between astrophysics and anthropology becomes. The sun that stirs magnetic storms also warms the caves where ochre paintings first appeared. The cosmic rays that travel through interstellar space may have triggered mutations in the ancestors of the artists who painted them. The idea that creativity could be an echo of solar turbulence doesn't diminish its wonder, it deepens it. It means that imagination might not be a uniquely human invention at all, but part of the universe's long habit of self-organization. We don't know, of course. It may turn out that our bursts of insight are purely homegrown, that the sun's influence on the brain stops at the warmth of daylight. But there's a strange comfort in considering that, at least in principle, some small part of human originality might be the Earth thinking with borrowed energy. So the next time you feel a spark of inspiration, when an idea seems to arrive from nowhere, electric and alive, maybe it does. Maybe the smallest part of it rode here on the wind of a solar storm, crossing 93 million miles of vacuum just to remind a primate species that energy loves to take new forms. It begins with a shadow that moves faster than any storm, silent and precise, sliding across the curve of the planet like a living thought. To those standing below it, the air shifts first. The temperature drops, birds falter, and colour drains from the world as if someone has pulled the light out of the sky. For a few impossible minutes, the sun becomes a black circle surrounded by a silver fire. It is one of the rarest, strangest spectacles available to human eyes, and for much of our history it was also one of the most terrifying. The word eclipse comes from the Greek eclipsis, meaning abandonment or forsaking. The ancients saw it as the moment the sun left us, perhaps in anger or exhaustion. Cultures across the world fill this darkness with meaning. Dragons devouring light in China, jaguars swallowing the sun among the Maya, wolves chasing the sky in Norse sagas. Each story recognized the same unease, that this wasn't night, but something pretending to be night. Daytime shadows remained, yet the stars appeared. The horizon glowed in all directions. The sun's warmth fled, but the air still shimmered faintly. It was, and still is, a contradiction in motion, a pause written into the machinery of heaven. For thousands of years we treated it as an omen. The Babylonians, meticulous sky watchers, were the first to realize it was also a pattern. They noticed that eclipses followed an 18-year cycle, now known as the Saros cycle. From that realization came the first predictive astronomy. What had once been a devouring monster became a clock. By the time of the Greek philosophers, the geometry behind eclipses was nearly understood. A perfect alignment between the sun, earth and moon. What astronomers call a syzygy. The moon's shadow sweeps across Earth at roughly 1 kilometre per second, fast enough that you can watch continents move beneath its path in satellite footage. The geometry is exquisite. The sun is about 400 times wider than the moon, but also about 400 times farther away, meaning they appear almost exactly the same size in our sky. This coincidence is temporary. The moon is slowly receding from Earth, about 4 centimetres each year. In roughly 600 million years, it will appear too small to cover the sun completely. Our epoch is lucky. Cosmic luck, really. We live in the brief window of planetary history when total eclipses are even possible. We evolved under skies where the sun could be perfectly masked for a heartbeat, revealing its hidden face. That face, the corona, is what scientists wait for. Normally invisible, it is the sun's outer atmosphere, millions of degrees hotter than its surface, and stretching hundreds of thousands of kilometres into space. No telescope or filter can quite replicate the view of it during totality. The light is silvery and alive, streaming in delicate filaments shaped by magnetic fields. During the 19th century, astronomers raced around the globe chasing eclipses, lugging telescopes and spectroscopes to remote locations for mere minutes of observation. In 1868, during an eclipse in India, French astronomer Jules Janssen recorded a spectral line that didn't match any known element. He thought he'd discovered something new, and he had. Helium, the second most abundant element in the universe, first seen in the sun before it was found on Earth. Every eclipse since has taught us something. We have used them to test Einstein's theory of general relativity, observing how starlight bends near the sun's mass. We have studied solar wind, plasma flows, and coronal heating. And yet, no matter how sophisticated the science, the emotional effect of standing under one hasn't changed much since those early myths. When the shadow reaches you, all language collapses. The world holds its breath. Animals freeze or grow confused, people cry without knowing why, and every instinct reminds you that something fundamental has gone wrong. Then, just as suddenly, it ends. The light returns with shocking speed, and the sky seems louder for it. During the total eclipse of April 2024, millions of people gathered along the path of totality, stretching from Mexico through the United States into Canada. It lasted only a few minutes, as always, but it joined continents in shared astonishment. Scientists captured high-resolution coronal data from aircraft, following the shadow at nearly its own speed, while others measured subtle changes in temperature, wind, and animal behaviour on the ground. But ask anyone who stood beneath it, and they'll describe it differently. A moment where time paused, where even thought seemed to dim. That stillness has always accompanied eclipses. Ancient writers called it the silence of the birds. It's a sensory reset, a temporary erasure of the familiar cues of daylight. Your brain, calibrated to brightness and shadow, doesn't quite know what to do. This mismatch, nightlight during day, creates an eerie calm that some psychologists compare to a mild trance state. It's not just darkness, it's a darkness that feels intelligent. The shadow's speed is part of the awe. Moving at over 3,000 kilometers per hour, it races faster than sound, faster than any wind. To the eye, it's not a gradual dimming, but a sudden wave rushing toward you, a dark horizon that devours the sun. Some eclipse chasers describe it as the only time you can see the shape of planetary motion. The moon's orbit expressed as a travelling absence. It reminds us that everything we consider still, the ground beneath us, the daylight around us, is constantly in motion. There's a strange humility in knowing that the same geometry that inspired fear and myth now guides satellites, calendars, and spacecraft trajectories. The syzygy that terrified early humans is the same alignment that allows for precision navigation between planets. What was once a dragon is now data. Yet even the most data-driven among us can't stand in that dim circle of totality without feeling something older than reason stir. The corona glows like a halo made of mathematics. For a moment we are small again, curious animals looking up, wondering why the world forgot itself. Eclipses also remind us of the layered nature of knowledge. The same event can be mythic and scientific, terrifying and enlightening, depending on how you look at it. In one sense, an eclipse is nothing more than light and shadow interacting with celestial mechanics. In another, it's a demonstration of scale, the delicate balance that allows us to exist between two bodies whose relative proportions just happen to create perfect symmetry in our sky. When that symmetry breaks for a few minutes, we glimpse the machinery behind the illusion of permanence. After totality passes, most people describe a kind of afterglow, not just in the literal light, but in the mind. It's as though the world briefly showed its clockwork and then closed the casing again. Perhaps that's why ancient astronomers devoted so much effort to predicting eclipses. They offered the only chance to see the sky think. Today, with simulations, satellites and live streams, the mystery has softened, but the emotional pull remains. Even in our age of constant screens, millions will still travel thousands of kilometres just to stand in that temporary darkness. They do it not just for the science, but for the sensation that, for a few minutes, the universe synchronizes with human experience. It is the most tangible reminder that we live on a moving world circling a moving star, accompanied by a moving moon, a cosmic choreography so perfect that it occasionally forgets which one of them is supposed to shine. And maybe that's the point. In every eclipse there's a whisper that order itself is fragile. The light we depend on can vanish at any moment, and yet it always returns. It's a rhythm older than civilization, an accidental ritual that binds physics to emotion. We measure it with telescopes, but we feel it with skin. When the next shadow crosses your sky, don't just watch the darkness. Watch the people around you fall silent. Watch the light retreat along the horizon, and the stars appear at midday. You're witnessing a moment that's both ancient and fleeting, a heartbeat in the dialogue between earth and sky. For all our equations, we're still children of that light, and its absence. Every few 100,000 years the earth inhales, and then it exhales. The rhythm is not one we can hear or feel within a single lifetime, but its effects have shaped every landscape, every coastline, every fossilized shore we have ever found. This breath of the planet is written in ice, in the frozen layers that advance and retreat, carving continents into the shapes we know today. The Earth has never been static. It tilts, wobbles, and drifts in its long dance around the sun. Those small changes in geometry, subtle shifts in the angle, distance, and timing of sunlight, are enough to decide whether the planet will freeze or thaw. The story begins about 2,400,000 years ago when something curious happened. Before then, the Earth had already known colder and warmer eras, but around that time the planet began slipping into a regular rhythm of great glaciations. Huge sheets of ice advanced from the poles, burying what is now North America, Europe and Asia beneath kilometres of frozen weight. Then, after tens of thousands of years, the ice melted back, seas rose again, and forests returned. This cycling between cold and warmth repeated itself, over and over, like the slow ticking of a planetary metronome. It's what scientists now call the Quaternary Ice Age, a time that technically includes today, because both Greenland and Antarctica are still crowned with permanent ice. The Serbian mathematician Milutin Milankovic was the first to translate this icy heartbeat into mathematics. Working in the early 20th century, long before satellites or digital models, he imagined Earth as a celestial pendulum, one whose rhythm was set not by weather but by the geometry of orbit itself. He calculated how sunlight, or insolation, varied over thousands of years due to three main factors: the shape of Earth's orbit, the tilt of its axis, and the wobble of that tilt through time. These became known as the Milankovitch cycles: eccentricity, obliquity, and precession. The slow, astronomical machinery that governs our seasons on scales so vast that no calendar could contain them. Eccentricity is the simplest to picture. The Earth does not orbit the Sun in a perfect circle, but in an ellipse that grows slightly more or less stretched over time. This stretch, caused by the gravitational tugs of Jupiter and Saturn, changes on a cycle of roughly 100,000 years. When the orbit is more circular, the difference between the closest and farthest points from the Sun, called perihelion and aphelion, is small, and the planet receives sunlight more evenly through the year. But when the orbit becomes more elongated, those differences grow. The Earth can spend longer periods farther from the Sun, allowing cooler summers and longer winters, the perfect conditions for ice to accumulate and linger. Then there is obliquity, the tilt of the Earth's axis relative to its orbit. Right now, our planet leans at about 23.5 degrees, giving us the familiar seasons. But that tilt isn't fixed. It rocks gently back and forth between about 22 and 24.5 degrees on a 41,000-year cycle. When the tilt increases, seasons grow more extreme, hotter summers and colder winters. When it decreases, seasonal contrasts soften, making high latitudes cooler overall. Small though these shifts seem, they change how sunlight is distributed, especially near the poles, influencing whether snow from winter survives the following summer. The third motion, precession, is perhaps the most elegant, a slow wobble, like a spinning top leaning as it turns. Over about 23,000 years, the direction of Earth's axis traces a wide circle in the sky, shifting where each hemisphere points during its closest approach to the Sun. This alters which season occurs at perihelion. Today, Earth reaches perihelion during the Northern Hemisphere's winter, slightly softening its cold. But thousands of years from now, that timing will reverse, giving the North hotter summers and colder winters. Precession on its own wouldn't cause an ice age, but combined with the other two cycles, it acts like a fine-tuning knob, amplifying or muting their effects. Together, these cycles control the flow of sunlight with astonishing precision. During periods when all three align to reduce northern summer warmth, snow that falls during winter fails to melt completely. Year after year, it builds into glaciers. Their whiteness reflects even more sunlight back into space, a feedback loop that deepens the cold. Then, when orbital geometry shifts again, sunlight strengthens, melting the ice and flooding the oceans. Each change is slow, yet over geological time, the effect is profound. Shorelines moving hundreds of kilometers, sea levels rising and falling by more than 100 meters, species migrating or disappearing entirely. Evidence for these cycles lies everywhere once you know how to read it. Layers of marine sediment record oxygen isotopes that track global ice volume. The ratio between heavier and lighter oxygen atoms changes with temperature and with how much water is locked up in glaciers. By measuring these ratios, scientists have reconstructed a continuous record of climate stretching back millions of years, and the pattern is unmistakable. Every 100,000 years, the signal dips and rises in near-perfect rhythm, matching 𝐓𝐈𝐌𝐄𝐒𝐓𝐀𝐌𝐏𝐒 calculations almost note for note. The match was so precise that when the data were first published in the 1970s, many called it one of the most elegant confirmations in the history of Earth science. It is humbling to think that something as abstract as orbital mechanics decides whether London is under ice or under rain. The continents themselves have drifted, mountains have risen and crumbled, yet this astronomical clock keeps ticking. Each tick lasts longer than the entirety of human civilization, yet we live inside it all the same. The last major glacial maximum peaked about 21,000 years ago. By then, sea level was so low that humans could walk from Siberia to Alaska, from Britain to mainland Europe. The ice sheets began retreating around 11,000 years ago, giving rise to the relatively stable climate we know as the Holocene, the warm intermission in which everything from agriculture to written language has unfolded. But even in this warmth, the clock hasn't stopped. The current configuration of Earth's orbit suggests we're slowly drifting toward conditions that would normally favour another glaciation tens of thousands of years in the future. If left entirely to natural forces, the planet would cool again. Snow would return to northern Europe, forests would shrink and glaciers would spread southward. It's an almost comforting thought, that nature operates on such grand patience, repeating patterns regardless of who or what is watching. Yet the very regularity that makes it predictable also makes it delicate. Small deviations can accumulate, tipping the system toward a new balance. The beauty of Milankovitch's idea is that it links human time to cosmic time. Every winter snowfall, every wave cutting at a cliff, is part of a slow-motion feedback between the sun, the earth, and the geometry of motion itself. The cycles remind us that climate is not chaos but choreography. The planet is never truly still. It's always adjusting, redistributing light and heat as it leans, wobbles, and swings through space. It's easy to see these cycles as mechanical, yet there's a quiet poetry in them. The tilt of a planet millions of kilometers away from its star decides the fate of forests, rivers, and eventually us. The precession of its axis, invisible to anyone without the patience of centuries, writes the script for future migrations. We like to imagine the seasons as something local, but they are written by celestial geometry. Every sunrise carries a trace of those ancient rhythms, and here's the most astonishing part. The mathematics predicted it all before the evidence was found. 𝐓𝐈𝐌𝐄𝐒𝐒 spent decades refining his tables by hand, calculating variations in solar radiation for each latitude, convinced that one day someone would confirm them with data. He never saw the full validation of his work, that came decades after his death. But his insight remains one of the most quietly powerful in science, that a planet's climate is, in large part, the poetry of its orbit. If you could speed up time and watch Earth's history unfold like a time-lapse, you'd see glaciers pulsing across continents like a slow heartbeat. You'd see deserts bloom, forests migrate, oceans retreat and return. From space, the ice would seem to breathe, exhaling warmth and inhaling cold. It's a dance choreographed not by gods but by gravity. And within that rhythm, all life has evolved, adapted, and occasionally vanished. The next time you look at a map of the world, try to imagine the invisible lines that shape it, the eccentric path that stretches and relaxes, the tilt that wobbles like a sleepy compass, the spin that precesses like a toy top. Every shoreline and mountain owes its outline to that slow geometry. Even our sense of what is normal, our weather, our seasons, our coastlines, is a temporary phase in a planetary oscillation that began long before us and will continue long after. If the sun is the heart of the solar system, then these orbital rhythms are its pulse. And though we can now model them precisely, their vastness still carries a quiet comfort. Because for all the chaos we create on the surface, beneath it there remains a clock that does not care who's watching. It just turns patiently, measuring ice and time in equal measure. If you want to know how warm the world was 100,000 years ago, there is no thermometer to check. The rocks don't talk. The oceans have forgotten most of their moods. But buried in the most fragile things on Earth, air bubbles, shells and snowflakes, the memory of climate remains, perfectly preserved. The planet records itself constantly. We just had to learn how to listen to ice and dust and calcium. Somewhere between chemistry and archaeology lies this strange science, reading the diaries that the Earth never meant to keep. The first entries in this record began long before us, written in atoms. When water evaporates from the sea, it carries two flavours of oxygen, the light isotope, oxygen-16, and the heavier oxygen, 18. The lighter one escapes more easily into vapour and falls back to Earth faster as rain. During colder times, when much of that precipitation turns into snow that never melts, the oceans become slightly richer in the heavier isotope. During warmer eras, the balance shifts back again. That small difference, nearly invisible, ends up fossilised in everything from ice cores to tiny shells on the ocean floor. Oxygen's subtle bookkeeping is what allows us to reconstruct the temperature of worlds that vanished millions of years ago. Let's start with the ice. When snow falls on the high plateaus of Antarctica or Greenland, it traps minute bubbles of air between its crystals. If that snow never melts, it compresses under its own weight, layer by layer, until it becomes ice. Each layer seals away the atmosphere of the year it fell. Its composition, its impurities, its whispers of carbon dioxide and methane. In places where snowfall is steady, those layers build into archives more reliable than any library. A single core drilled from the East Antarctic ice sheet can reach more than 3 kilometers deep, representing almost 1 million years of atmospheric history. The process of reading it is painstaking. Scientists extract a slender cylinder of ice and slice it into sections barely thicker than a coin. Each slice is melted in vacuum chambers, releasing ancient air to be analysed by mass spectrometers. From those bubbles they can tell how much carbon dioxide floated in the atmosphere, how much dust blew from distant deserts, even whether volcanoes erupted that year. In the ice's crystalline structure itself, the ratio of heavy to light oxygen reveals the temperature of the snow when it first fell. It's as though every snowflake carried a microscopic thermometer inside. The story these cores tell is one of rhythm and resilience. You can see the glacial cycles written plainly, the rises and falls of temperature every 100,000 years, perfectly matching the orbital patterns described by 𝐓𝐈𝐌𝐄𝐒𝐓𝐀𝐌𝐏𝐒. You can also see shorter, sharper swings, abrupt warmings that occurred in mere decades, volcanic winters that briefly cooled the world, sudden bursts of methane from thawing permafrost. The precision is breathtaking. In some cores, individual years can be distinguished like tree rings, each line a breath of the planet. But ice is only half the archive. When glaciers form, oceans respond. Marine sediments are where the deeper memory of the planet resides, not in frozen air, but in the bodies of microscopic creatures. Foraminifera are single-celled organisms that build tiny shells from calcium carbonate. When they die, their shells rain down onto the seafloor, forming layers of mud that harden over time into limestone or chalk. Inside those shells, oxygen isotopes are locked in the same ratios that existed in the seawater of their day. By measuring them, scientists can reconstruct ocean temperatures going back tens of millions of years, far beyond the reach of ice. Some of these records stretch back to the time of the dinosaurs, showing periods when tropical seas reached 30 degrees Celsius and polar regions were warm enough for crocodiles. Others trace the slow cooling that began around 55 million years ago, when the newly formed Himalayas began to draw down atmospheric carbon dioxide through chemical weathering, and the Antarctic continent drifted over the South Pole to grow its first permanent ice cap. In every case, the data come not from fossils of beasts or trees, but from shells no larger than grains of sand. There is something quietly poetic about that. The grandest changes in climate, the rise and fall of ice ages, the opening and closing of oceans, are revealed by the tiniest witnesses. The same is true for plant life on land. As vegetation spread across the continents, it began pulling carbon dioxide out of the air, storing it in wood and soil. During the Devonian period, about 400 million years ago, the first deep-rooted plants evolved, stabilizing riverbanks and accelerating the burial of organic carbon. That revolution, sometimes called the greening of the Earth, may have cooled the planet dramatically, triggering one of the earliest global glaciations. Later, vast forests of the Carboniferous period locked away so much carbon in peat and coal that oxygen levels in the atmosphere soared, supporting giant insects and amphibians. The balance between what plants breathe in and what volcanoes and decay release has been the main thermostat of the planet ever since. Even now, when we talk about greenhouse gases, we're still talking about the legacy of that ancient dialogue between rocks, roots, and air. If you trace the isotopic records together, the ice cores, the deep-sea sediments, the mineral layers, they form a continuous symphony of temperature and chemistry spanning the last 4.5 billion years. Early Earth was hellishly hot, its air thick with carbon dioxide and methane, oceans boiling under a dimmer sun. Then came the first great cooling, perhaps as photosynthetic microbes began to bloom and release oxygen. Around 2.5 billion years ago, that transformation, the Great Oxidation Event, left unmistakable traces in rocks. Iron formations rusted red, and new isotopic signatures of sulfur appeared, marking the planet's first breathable sky. From then onward, the Earth's climate has swung between greenhouses and icehouses, each recorded in the ratios of oxygen, carbon, and hydrogen in ancient minerals. During greenhouse periods like the Cretaceous, warm oceans produced lighter oxygen signatures. During ice ages, heavier ones prevailed. Every coral reef and stalactite, every band of chalk on a cliff, adds another data point to the world's slow autobiography. The Holocene, the warm phase we currently inhabit, is a mere footnote by comparison, only about 11,000 years long so far. Yet even within it, ice cores and pollen records show smaller pulses, brief cooling events, shifts in monsoon intensity, migrations of forests. In Greenland's Aya, one can see traces of the Younger Dryas, a sudden return to glacial cold around 12,800 years ago, possibly triggered by a flood of meltwater disrupting ocean currents. It lasted barely a millennium before warmth returned, ushering in the stable climate that allowed agriculture to emerge. To look at these archives is to realise that stability is an illusion. The Earth has always been changing, always experimenting with new balances. But what the record also shows is continuity, a planet that remembers. Each shell and snowflake stores its moment, adding it to an unbroken chain of evidence that connects us to a molten beginning and a living present. The science that decodes these clues is itself a human triumph of patience. When the first deep cores were drilled in Greenland in the 1950s, some scientists doubted that ancient air could survive intact. It did. When isotopic ratios from ocean sediments were first compared to theoretical predictions, the match was almost too good to believe. It was as if nature had kept its own notes and was waiting for us to learn the language. Even with all we know, there are mysteries left. Some transitions in the record, abrupt spikes and dips, defy easy explanation. Were they caused by changes in ocean circulation, volcanic activity, or something we haven't imagined yet? Each new core, each new isotope study refines the story, but the picture remains dynamic, as if the planet was still editing its autobiography. The deeper lesson in these frozen and fossilized memories is humility. The climate is not a static backdrop for life, but a living system, shaped by the very organisms that inhabit it. The shells that record temperature were made by creatures that depended on it. The ice that traps our atmosphere also reflects sunlight and shapes weather. Life and climate are two sides of the same coin, written together in isotopic ink. Somewhere under our feet, and deep beneath the polar caps, the next pages are already being written. Layers of snow falling tonight, dust settling on ocean floors, tree rings forming in silence. They will be read one day by other scientists, maybe other species, trying to remember what the world was like in our time. They will find our century marked clearly, just as we found the ancient ones marked before us. The Earth forgets nothing, it only waits for patient eyes to ask. For hundreds of thousands of years, the Earth's temperature moved in slow waves, peaks and valleys that took entire civilizations' worth of time to form. The last 10,000 years, the period we call the Holocene, were unusually calm. The ice had retreated, the seas had settled, and the planet found a rare equilibrium. Into that stability we were born. Then, somewhere around the middle of the 19th century, the line on the graph began to curve upward. Not gradually, as it always had before, but suddenly, almost violently, within the span of a single lifetime. For the first time in geological history, the planet's thermometer jumped, not because of tectonic drift or orbital rhythm, but because of something moving on its surface. If the Earth's past climate is a symphony written in millennia, then the last century is a drumbeat, too loud, too fast, too sudden to fit the score. Scientists first noticed it not through intuition, but through data. When global records of temperature were compiled, the pattern was unmistakable. From about 1850 to the present, the average global surface temperature has risen by more than 1 degree Celsius. That might sound modest, but measured against the planet's long, patient pulse, it is a vertical leap, a century that moved the needle as much as the previous 10,000 years combined. To make sense of such a sudden change, researchers did what they always do. They looked for cycles. Could this be another Milankovitch fluctuation, another swing in the geometry of the Earth's orbit? But orbital changes take tens or hundreds of thousands of years to unfold, not decades. They are the slowest gears in the solar clockwork, their effects smeared across ages. A 1 degree jump in a single century is not their language. Perhaps, then, a cosmic cause. The Sun, our ultimate source of warmth, does vary in intensity through its 11-year cycle of sunspots and magnetic reversals. Yet the solar output, measured carefully since the late 20th century, shows no long-term increase matching the modern warming trend. In fact, solar irradiance has remained remarkably stable. When researchers compared the two curves, solar activity and global temperature, they diverged rather than aligned. The sun had not grown brighter, something else had. Volcanoes, another usual suspect, can and do change the climate, though they tend to cool rather than heat. large eruptions inject reflective aerosols into the stratosphere, shading the planet for a few years at a time. The eruption of Mount Tambora in 1815 triggered the year without a summer, a brief global chill that withered crops from China to Europe. But volcanic effects fade quickly. Over the last century and a half, volcanic activity has not increased. If anything, it has offered short interruptions to the warming, not the cause of it. Could it have been a meteor, like the one that ended the age of dinosaurs 66 million years ago? That kind of impact would leave clear geological evidence: a crater, a global dust layer, spikes of iridium in sediments. None exists for the modern age. The rocks are silent. No cosmic visitor has struck the planet since humans began charting the skies. If the traditional drivers of climate change cannot explain this spike, the only place left to look is the thin layer of atmosphere itself, that fragile veil of gases we live within. And that is where the story becomes uncomfortable. The ice cores that have preserved our past climates also preserve the fingerprints of this new one. When scientists drilled into Greenland and Antarctica, they not only found temperature records, but also trapped air from ancient atmospheres. The ratio of carbon dioxide and methane in those bubbles follows the temperature almost perfectly. When one rises, so does the other. In those ancient layers, carbon dioxide levels rarely climbed above 300 parts per million. Even during the warmest interglacials, the highest peaks were still below today's minimums. But starting around 1850, the trapped air begins to show a sharp and unprecedented increase. By 1950, it had already crossed 310 parts per million. By the turn of the millennium, it passed 370. Today, it hovers above 420, a level not seen on Earth for at least 3 million years, when the world was several degrees warmer and sea levels tens of meters higher. Methane, a more potent though shorter-lived greenhouse gas, tells a similar story. Its concentration nearly tripled since the pre-industrial era. Both gases share the same isotopic signature, a chemical fingerprint that traces them back to living carbon, to fossil fuels and agriculture, not to volcanoes or the deep mantle. The evidence measured independently by laboratories around the world points to the same origin: us. The physics behind this link is not mysterious. In the laboratory, carbon dioxide and methane are known to absorb infrared radiation, the very wavelength that Earth emits to space as it cools. That knowledge dates back to experiments by John Tyndall in 1859, the same year Charles Darwin published On the Origin of Species. Tyndall demonstrated that these gases, though invisible, act like blankets in the atmosphere, trapping heat. Later, in 1896, Swedish chemist Svante Arrhenius calculated that doubling the amount of carbon dioxide could raise global temperatures by several degrees. His numbers, written by hand in the age of oil lamps, match modern climate models astonishingly well. For decades, those calculations were little more than curiosities. The planet seemed too vast, the sky too boundless, for human industry to matter. But the Industrial Revolution had already begun to prove otherwise. As coal, oil, and later gas became the engines of progress, the byproduct of that progress, carbon dioxide, began to accumulate. The chemistry was invisible, the consequences delayed, but the effect inexorable. By the mid-20th century, scientists started measuring atmospheric carbon directly. Atop the Mauna Loa Observatory in Hawaii, Charles Keeling began daily readings in 1958. His graph, now called the Keeling curve, showed a steady annual sawtooth pattern. Carbon levels rising each winter as plants died, falling slightly each summer as they grew again, but trending relentlessly upward year after year. When compared with global temperature records, the alignment was unnerving, a perfect parallel climb. It's difficult to appreciate how abnormal that curve is without seeing the full context. Over the last 800,000 years, carbon dioxide levels fluctuated naturally between about 180 and 280 parts per million, synchronized with the ice ages. Those rises and falls happened slowly, driven by orbital cycles and biological feedbacks, taking thousands of years. The modern increase happened in less than 200. Nature's graphs slope gently, ours spike vertically. Some skeptics once argued that temperature leads carbon, not the other way around, that warming oceans release carbon dioxide, which then amplifies the trend. In past natural cycles, that was often true, but this time, the timing is reversed. The carbon rise came first, unmistakably traced to the combustion of fossil fuels, cement production, and deforestation. It's as if the usual dance between Earth and atmosphere had been flipped. The partner that once followed is now leading. Even the isotopes within the carbon tell the story. Fossil carbon, long buried underground, lacks the radioactive isotope carbon-14, which decays over time. Modern atmospheric samples show a clear decline in carbon-14 relative to other isotopes, meaning that a growing share of the air's carbon is ancient, released from fuels that have been sealed away since the Carboniferous period. Every car, every chimney, every power plant exhales that ghostly breath from 300 million years ago, and the sky records it faithfully. The magnitude of the shift is not just chemical but thermal. Heat, like carbon, accumulates. The oceans have absorbed more than 90% of the excess warmth added to the system. They are expanding, rising, and storing energy that will take centuries to dissipate. The cryosphere, the frozen parts of the planet, is responding as well. Satellite measurements show glaciers shrinking worldwide, Arctic sea ice retreating, and Greenland's mass balance tipping from gain to loss. These are not theoretical changes, they are measured ones, precise down to millimeters and degrees. If the climate of the past was a pendulum swinging between warm and cold, the present is a lever pulled sharply in one direction. The rate of change matters as much as the magnitude. Species and ecosystems evolved under the slow pacing of natural cycles. The current acceleration leaves them little time to adapt. Coral reefs bleach, permafrost thaws, migration patterns shift. The Earth, which once took millennia to warm or cool by a degree, is now doing so in decades. This isn't a story of panic, but of proportion. The numbers are small, a few parts per million, a few degrees, yet their significance is vast because the planet's systems are finely balanced. A 1-degree global average rise means entire regions warming by several, oceans expanding, ice vanishing. It means the end of the Holocene stability that cradled human civilization. And so, the graph stands there like a confession. It doesn't accuse, it simply shows. The upward curve from 1850 onward is so steep that it looks out of place against the rest of Earth's climatic history. It's the kind of anomaly that, in any other dataset, would make a scientist suspect an error, until every independent line of evidence confirms it. Ice, air, sediment, satellite, thermometer, all whisper the same thing. Something fundamental has shifted. We still don't know every consequence. The climate system is complex, full of feedbacks and delays, but the signature is clear enough to read. This is not the rhythm of the sun or the geometry of the orbit. This is something new, something self-made. In the long memory of the planet, the past century will appear as a thin, bright line of disruption, the moment when the graph spiked and did not return. There are moments when the planet seems to inhale and exhale in unison with us. The slow breath of trees, the quiet rhythm of seasons. For billions of years, photosynthesis has been the planet's most reliable transaction, a steady exchange of light and life. Plants take carbon dioxide, use it to grow, and in return give back oxygen. It's a simple promise that built everything breathing today. But recently that promise has begun to break. Forests, once the lungs of the Earth, are catching fire, and instead of storing carbon, they are releasing it. The air that once smelled like rain and resin now carries the scent of its own undoing. It's a strange twist in the story of photosynthesis. After hundreds of millions of years of storing sunlight in wood and leaf, the planet has started giving it back, all at once, through flame. Scientists call it fire feedback, though the phrase sounds almost too calm for what it describes. It means that the climate system, which once absorbed carbon through forests, is now amplifying its own warming because those same forests are burning faster and hotter than at any time in recorded history. The modern acceleration began quietly in the mid-20th century, when large-scale fire suppression policies in North America and Eurasia were introduced to protect timber and settlements. For decades that seemed successful. Fewer visible fires, more standing forest. But beneath the surface, fuel accumulated, dead wood, dry underbrush, and the legacy of warming seasons. When the balance tipped, it tipped violently. Since the 1950s, the number and intensity of the large wildfires in boreal regions, those vast northern forests stretching across Canada, Alaska and Siberia, have surged. Satellite records now show the Arctic burning on a scale once thought impossible. What makes these fires extraordinary isn't just their size, but their speed. They burn through permafrost-rich soils and peatlands that have remained damp for thousands of years, releasing carbon that had been stored since the last ice age. In some cases, they reignite months later from underground, earning the eerie name zombie fires. These blazes do not simply consume trees, they consume time. Measurements from boreal fire seasons over the past 2 decades reveal a staggering reversal in carbon balance. Canada's wildfires, for example, have released hundreds of megatons of carbon dioxide annually, rivaling the country's industrial emissions. In 2023, the record-breaking season emitted more than 1 billion tons, making Canada's forests, once a sink, temporarily one of the largest sources of carbon on Earth. The irony is sharp enough to sting. Photosynthesis is returning its deposit. The pattern is global. In the Amazon, deforestation and prolonged droughts have turned parts of the rainforest from a net absorber to a net emitter of carbon dioxide. Trees that once created rain through their transpiration cycles are now dying faster than they can regenerate, weakening the atmospheric rivers that feed them. In Australia, the Black Summer of 2019 to 2020 scorched more than 20% of the country's forests, releasing around 800 million tons of carbon dioxide, equivalent to the annual emissions of industrialized nations. Smoke from those fires circled the planet, dimming sunlight in South America and creating its own weather, even in regions once thought immune to large-scale burning, such as Scandinavia and the British Isles. Hotter and drier summers have begun to awaken dormant fire seasons. Lightning ignitions in the Arctic Circle, an event once statistically negligible, are now recorded almost every year. The tundra, once frozen and safe from flame, has started to burn. When organic soil in those regions catches fire, the damage extends beyond vegetation. The underlying permafrost thaws, releasing trapped methane, a greenhouse gas roughly 80 times more potent than carbon dioxide over short timescales. That thaw forms another loop in the feedback chain. Fire darkens the surface with soot, reducing albedo, the planet's reflectivity. With more sunlight absorbed, the ground warms faster, thawing deeper permafrost layers and drying surrounding peat. Drier peat burns more easily, releasing still more carbon. It's a self-reinforcing circle, not apocalyptic but quietly relentless. What begins as weather becomes chemistry. What starts as local tragedy becomes part of planetary arithmetic. The physics of it are soberingly simple. Each gram of carbon released into the atmosphere from burning biomass adds to the total pool of greenhouse gases. Because atmospheric carbon mixes globally within months, a tree burned in Siberia contributes to the warming that dries the Amazon, which fuels fires that in turn accelerate Arctic melt. The system is not linear, it's recursive, and every new blaze makes the next one slightly easier to ignite. The feedback isn't only chemical, it's ecological. Many forest species are adapted to periodic fires, pines that need heat to open their cones, grasslands that regrow stronger after burning. But the frequency and intensity now exceed the recovery rate. In some boreal zones, repeated fires prevent seedlings from establishing at all, leaving behind shrubland or bare mineral soil. That shift from dark conifer forest to lighter scrubland further reduces carbon uptake and changes how sunlight is reflected, adding another layer to the feedback. Satellite observations have allowed scientists to watch this transformation almost in real time. Using thermal imaging and atmospheric sensors, they can trace fire plumes, estimate carbon emissions, and even detect the regrowth that follows. The data show clear trends. Fire seasons are longer, ignition points more frequent, and average burn area increasing dramatically since the 1980s. Global burned area has declined slightly overall because of agricultural expansion in some regions, but the fires that remain are more severe and carbon intensive. It's not about the number of flames, it's about their ferocity. In the Northern Hemisphere, the connection between temperature anomalies and fire activity is now statistically undeniable. Each additional degree of warming sharply increases the probability of extreme fire weather, combinations of low humidity, high wind and heat. The atmosphere itself becomes more flammable, drying vegetation faster than rain can replenish it. What once counted as a rare event, a so-called megafire, has become annual in parts of California, Siberia, and Australia. It's tempting to imagine that forests will grow back and recapture the lost carbon, and some will. But regrowth takes decades, and in the meantime the released gases continue to warm the air. Fires also change the nutrient balance of soils, sometimes locking them into cycles of erosion and infertility. In peatlands, where organic matter can take thousands of years to accumulate, a single burn can erase millennia of storage. It's like deleting chapters from the planet's carbon diary. The scale of the transformation is perhaps best seen from space. Satellite images of Siberia in late summer now show vast ribbons of smoke stretching thousands of kilometers, drifting across continents. The smoke particles reflect sunlight and can temporarily cool regions below, masking part of the warming they cause. But as the aerosols settle, their effect fades, while the carbon dioxide they carried remains for centuries. It's a trade the atmosphere never agreed to. What makes this feedback unsettling is that it blurs the line between natural and artificial. The fires are often ignited by lightning or local land use, but their intensity and persistence are driven by conditions humans helped create. Hotter, drier air, longer summers, shorter winters. Once started, they operate independently, like an ecological machine that no longer needs our hand to turn the crank. Still, amid the metrics and smoke, there is perspective to be found. Fire is not an invader. It's an ancient force, older than our species, essential to many ecosystems. It clears debris, releases nutrients, resets growth. The problem is not its existence, but its imbalance. Too much energy in the system, too fast for the biosphere to absorb. Fire has always been the planet's way of exhaling. It's only now that we've made it hyperventilate. Scientists studying these feedback loops speak with both precision and restraint. They don't talk in apocalypse, but in probabilities. The increased odds of runaway feedbacks, the thresholds where sinks become sources. Yet behind the technical language, there's a quiet astonishment. The carbon cycle, once the great stabilizer of life, is now turning in reverse. Forests built by sunlight are burning fast enough to change the composition of the very air we breathe. And still, the Earth continues to breathe, through what remains of its forests, its soils, its oceans. Each inhale and exhale is now tinged with smoke. The planet has begun to tell us in flame and chemistry that the old equilibrium has been disturbed. Whether this is a temporary fever or a long transformation, we can't yet say. But one thing is clear: when the lungs of the Earth catch fire, the atmosphere listens. Every creature on this planet is in motion, whether it knows it or not. Life has always been a traveller, crossing oceans, climbing mountains, waiting out the cold, or chasing the light. But never before has movement been required so quickly, so relentlessly, on such a crowded planet. In the past, species migrated with the slow grace of geological time. Forests could shift hundreds of kilometres over thousands of years, following the retreat of ice or the spread of rain. Now, the climate itself is moving faster than most of life can walk, fly, or seed. What happens when evolution's marathon turns into a sprint? The climate zones that shape ecosystems are not stationary. They are boundaries drawn by temperature and rainfall, and those boundaries are shifting. Over the last century, the lines on climate maps have drifted toward the poles at an average of about 100 kilometres per decade on land, and even faster in the oceans. It's as if the tropics have loosened their grip and begun sliding north and south, dragging with them every species that depends on their warmth. Mountains are seeing similar escalations. Species that once thrived at lower elevations are now climbing hundreds of meters upward each generation, following the receding cool. For plants rooted in place, that climb may as well be infinity. Ecologists now use the phrase climate velocity to describe this phenomenon, the speed at which a species must move to stay within its preferred temperature range. Some organisms can keep pace, mobile animals, fast-breeding insects, and some fish. But for many the math is brutal. A tree that spreads its seeds a few meters each year cannot match a climate line that races hundreds of kilometers in a lifetime. The world is effectively redrawing itself faster than its inhabitants can rewrite their genes. There are success stories. though they come with quiet irony. Butterflies in Europe have been expanding their ranges northward, some by as much as 200 kilometres in a few decades. Boreal fish species, once confined to cold subarctic waters, now swim farther north than they have in thousands of years. Arctic foxes retreat ahead of red foxes invading from the south. In the high Alps, plants are colonising peaks that were once too cold for photosynthesis, only to find nowhere higher to go. The pattern repeats everywhere, migration until there's no further up, no further north, no further deep to escape into. The oceans too are on the move. Marine species respond to temperature even more directly than land dwellers, because their environment changes as fast as the water currents shift. Over recent decades, entire fish populations have migrated poleward: cod, mackerel, sardines and plankton, reshaping fisheries and altering ecosystems thousands of kilometres apart. The North Sea, once dominated by cold water species, now hosts creatures formerly found in the Bay of Biscay. Coral reefs, which rely on narrow thermal thresholds, are trying to re-establish themselves in cooler waters, sometimes successfully, sometimes not at all. Bleaching events now mark the edges of that failure, like the ghostly signatures of a species outrunning its tolerance. What's happening isn't new in kind. Life has always adapted to change, but it is new in speed. During the last major deglaciation about 12,000 years ago, as the world warmed naturally after the Ice Age, ecosystems shifted roughly 10 to 100 times more slowly than they are moving today. Evolution could keep up. Mutations, dispersal, and natural selection had time to work. Now, the pace of warming compresses evolutionary time into ecological panic. Traits that once helped survival over centuries must appear within decades, or not at all. The mismatch between climate velocity and biological response is what ecologists call extinction debt. It means that many species alive today are already effectively extinct. They just haven't vanished yet. Their habitats are disappearing too quickly for them to adapt, but inertia, longevity, and chance delay the outcome. Trees still standing in forests that will no longer suit their seedlings are living in borrowed time. Coral reefs may appear vibrant even as their larvae fail to settle in overheated waters. The world, in other words, carries ghosts of species not yet gone but already sentenced. This doesn't mean all is lost. Life is astonishingly inventive. Evolutionary biologists have documented cases of rapid adaptation within single generations. Insects shifting their breeding cycles, birds adjusting migration timing, fish altering their thermal tolerance ranges. But adaptation has limits. Temperature, oxygen, acidity and rainfall form a tight physiological web that can't be rewoven indefinitely. For many species, it's not a question of adaptation, but of escape. Some ecosystems act as corridors for that escape. Mountain ranges, rivers, coastlines. These are the routes through which life attempts to reroute itself. But human geography complicates the path. Roads, cities, farmland and fences fragment the landscape, creating barriers where once there were gradients. Even if a forest tries to migrate north through seed dispersal, it may find only highways. Some animals can navigate around those obstacles, others can't. Habitat fragmentation turns climate migration from a race into a maze, and so, scientists have begun to map potential climate refugia, places where microclimates, elevation, or unique geography might offer stable conditions despite global shifts. Deep valleys, shaded slopes and upwelling ocean zones can act as temporary sanctuaries, allowing species to linger while the broader climate changes around them. These refuges are not permanent. They are pauses in a storm, but they could buy time, perhaps enough for evolution to catch its breath. The irony is that some of the most ancient species, those that survived previous extinctions, may finally reach their limits now. Horseshoe crabs, which have outlived ice ages and asteroid impacts, depend on coastal wetlands now threatened by rising seas. Amphibians, already sensitive to small temperature and moisture changes, face both fungal disease and shifting rainfall patterns. Even microbes, the most adaptable of all, are shifting their distributions. Soil bacteria from tropical regions moving northward, altering the chemistry of entire ecosystems. It's tempting to imagine that biodiversity will simply reshuffle, that for every species lost, another will move in. But ecosystems are not interchangeable puzzles. Relationships built over millennia can unravel in a single misplaced season. Pollinators arrive before flowers bloom. Migratory birds reach feeding grounds after insects have already hatched. Predator and prey lose synchronization. The result is a quiet chaos. Species still present but misaligned, existing in the same space but no longer in the same time. Even the winners of this race face uncertain futures. Species that expand their range often encounter new diseases, competitors, or prey they are unprepared for. Invasive species thrive in this disarray, capitalizing on the gaps left behind. In a warming world, mobility becomes an evolutionary advantage, but not always a good one. Some fast-moving species destabilize ecosystems by outcompeting slower ones. Evolution rewards speed, but not necessarily harmony. When viewed from space, the biosphere appears calm. Forests still green, ocean still blue. But beneath that calm, the boundaries of life are in flux. Satellites now detect vegetation shifting northward at measurable rates. Pollen studies show changing compositions year by year. The Arctic tree line, once held in place for centuries, advances visibly within a human lifetime. Even the microbial ecosystems in soil and ice are reorganizing, changing how carbon is stored and released. The Earth's surface is not just warming, it's rearranging its biology in real time. There is a strange kind of empathy in studying this motion. Every creature that moves is doing what we would do, trying to survive, following comfort, chasing equilibrium. There's no villain in a migrating butterfly or a starving polar bear, only the logic of biology colliding with the velocity of physics. The planet is not dying, it is changing, and change has always meant loss and renewal in unequal measure. The question is not whether life will continue, but what form it will take when it finds new homes in unfamiliar places. The fossil record offers perspective, if not comfort. During past warming events such as the Paleocene-Eocene thermal maximum, 56 million years ago, ecosystems reorganized profoundly, but eventually stabilized. It took tens of thousands of years. Species migrated, evolved, and filled new niches. The difference is that this time, the acceleration is faster and the world smaller. There are fewer corridors left, fewer untouched refuges. The evolutionary clock ticks the same, but the landscape beneath it is running ahead. What we're witnessing now is a new phase in the story of life. Not extinction alone, but redistribution. The biosphere is in motion, resorting itself according to new rules. It's the same instinct that carried our own ancestors across continents, the same will to live that defines everything that breathes. Adapt or vanish, a phrase as old as evolution itself, now spoken again by the forests, the reefs, the wings that cross warmer skies. There is another layer to this planetary reshuffling, one that hides in the genetics of the survivors. As habitats fragment and populations move, the connections between once-linked groups begin to break. In evolutionary terms, isolation is both a curse and a catalyst. Small, separated populations lose genetic diversity quickly. Inbreeding and random drift make them fragile. Yet isolation can also spark new adaptations. Subtle genetic experiments happening in parallel as species scatter. What was once a continuous forest may become a patchwork of evolutionary laboratories, each testing a different solution to the same rising heat. The pace of these genetic changes is astonishingly uneven. Some plants are already evolving heat-tolerant enzymes or altered flowering times. Some insects are developing shorter life cycles to match warmer seasons. Others lag behind by just enough to make survival mathematically unlikely. Evolution is still working, but it's being forced to sprint in a race designed for walking. Migration is not only biological, it is geographical memory rewritten. Every ecosystem carries a long fossil echo of where it has been before. Pollen grains buried in lake sediments show that oak and spruce forests once reached far beyond their current ranges, chasing past climates across continents. Now the same experiment repeats, only faster and under constraint. Seeds ride on wind, hooves, and human trade routes. Algae drift through warming currents to colonize new coasts. Even microbes in the air, invisible, weightless travelers, are shifting their domains, riding thermal updrafts toward poles and mountains. It is the largest redistribution of life since the end of the last ice age, and it is happening quietly beneath headlines, season by season. Some scientists describe this moment as a reorganization of the biosphere rather than a simple loss. Species are mixing that have never met before. Mountain plants encountering coastal insects, tropical fish sharing space with cold water plankton. The results can be unpredictable. New symbioses, new competitors, and sometimes new pathogens. This mixing is evolution's raw material, but it comes with risks that ecosystems haven't rehearsed. When the ranges of species overlap in ways they never did before, old balances dissolve. A predator introduced into a new food web can unravel decades of ecological equilibrium. Yet within that chaos lies the possibility of invention, hybrid zones, rapid evolution, and entirely novel communities of life forming in places that were once considered stable. At the planetary scale, these transitions blur the boundaries between past and future biomes. The Arctic, once white and silent, now hosts grasses, shrubs, and insects migrating north. Tropical mountain slopes, where cool refugees once persisted, are shrinking like islands in a warming sea. Each of these shifts rewrites the biological map of the world, not through extinction alone, but through replacement, overlap, and transformation. Life is improvising, and we're watching that improvisation unfold in real time. Perhaps the most humbling realization is that migration is not a problem for life. It is its oldest instinct. What's new is the speed at which the stage beneath it is tilting. Species are moving not because they want to, but because stillness has become fatal. And as they go, walking, flying, blooming, drifting, they carry with them fragments of the ecosystems they leave behind. In this sense, every migration is an act of memory. Each step north, each seed carried by wind, is life trying to remember where stability once was and where it might be found again. If you step back far enough, past the lines on weather maps, past the centuries of records, past the span of even a species' memory, you begin to see that Earth has never stopped speaking. Its rhythms are ancient, its voice layered in frequencies so low and slow that a single lifetime barely registers as a pause between words. For most of human history, we mistook those silences for stillness. Now, after centuries of invention, acceleration, and distraction, we're beginning to notice the background pulse again, the sun's breath, the moon's pull, the magnetic murmur beneath our feet, and the long mathematical sways of orbit and ice. The question is not whether Earth has a future. It always will. The question is whether we have learned enough soon enough to take our place within its tempo instead of stumbling against it. Every cycle we've uncovered, solar, lunar, magnetic, orbital, teaches the same lesson in a different language. The sun reminds us that constancy hides in change. Its steady light flickers with an 11-year heartbeat. The moon shows us that small angles repeated patiently can lift oceans and reshape coasts. The magnetosphere tells us that even invisible forces hold the world together, and that reversals, though disorienting, are part of continuity. The slow geometry of Earth's orbit, its tilts and wobbles over tens of thousands of years, teaches us that climate itself is a choreography, not a fixed setting. Each of these cycles is larger than us, indifferent to our politics and timetables. Yet we've now reached the point where our own actions form a cycle too, one measurable in the chemistry of the air and the temperature of the sea. We have become, in effect, a new layer of planetary feedback. The Intergovernmental Panel on Climate Change calls the coming centuries the long tail. Even if all carbon emissions stopped tomorrow, much of the heat we've added would remain, slowly redistributing through ocean currents and atmosphere for hundreds of years. Some of that warmth will raise seas, some will alter rainfall, some will simply hum quietly in the background as the planet finds a new equilibrium. The time horizon is beyond our political cycles, beyond our lifespans, but not beyond our influence. 1,000 years from now, if any eyes remain to watch the sky, they may still see the traces of this century written in the tilt of glaciers and the shape of the coasts. It's not a punishment, just physics, the delayed echo of a civilization breathing faster than its planet. And yet, there is a subtle hope in that recognition. Knowing that the world responds to us is proof that we are not separate from it. For the first time, perhaps, an intelligent species has measured its own feedback loop in real time and decided to change course. That act, awareness followed by restraint may be as rare in the universe as life itself. Across laboratories and power plants, deserts and coastlines, the idea of net zero is less a policy than a new evolutionary adaptation, learning to metabolize energy without breaking the system that sustains us. Carbon capture projects, reforestation programs, renewable networks, all of these are attempts to turn human ingenuity inward, to redesign our metabolism so that civilization can coexist with the slow pulse of Earth, rather than constantly racing ahead of it. None of this guarantees success. The numbers are daunting, the politics chaotic, and the physics uncompromising. But life has always survived by improvisation, and humans are particularly good at it. We learned to read the stars to navigate oceans. Now we're learning to read the atmosphere to navigate the future. The same curiosity that once lit fires in caves and sent machines to Mars is the same that might yet stabilize the air above our heads. The difference is that this time, the experiment must be gentler. It requires listening as much as acting, tuning ourselves to a tempo measured in centuries instead of election cycles. When scientists speak of planetary boundaries, they mean the thresholds beyond which ecosystems become unpredictable. But boundaries also imply edges, and edges are where awareness grows. In the last few decades, as satellites began watching Earth continuously, we've developed something like a planetary nervous system. We can see the planet breathe, the rise and fall of carbon dioxide with the seasons, the flicker of city lights across night, the migration of clouds over a spinning sphere. In that sense, modern science is not just observation, it's empathy scaled up to a planet. We're learning what it feels like to live inside a system rather than on top of it. Maybe that's what maturity looks like for a species, realizing that dominance was always an illusion, that survival depends on rhythm, not rule. The cycles that once seemed external are in a quiet way internal too. The magnetic field that shields us is born from molten movement beneath our feet. The tides that rise and fall with the moon tug at the water in our own cells. The 11-year flare of the sun ripples faintly through our biology. We are participants in a symphony we didn't compose but have always played in. Looking ahead 1,000 years, it's impossible to say what form civilization will take, or whether it will still use that word. Continents will look different. Rivers will reroute. Some species will vanish. Others will fill the spaces they left. But if knowledge survives, so will humility. The understanding that Earth's cycles are not obstacles to overcome but teachers to learn from. Climate, magnetism, light and shadow. They are the planet's way of keeping time. And time, if you listen closely, is still on our side, provided we learn to move with it. So maybe the long forecast is not a prediction at all, but an invitation. To think beyond the horizon of self, to treat every degree of warming as both warning and possibility, to remember that we are temporary guests on a world that has survived worse than us and will outlast us. The sun will continue its quiet reversals. The moon will continue to pull the tides. The planet will continue to turn its molten core like a slow drumbeat. What happens in the thin film of life on its surface depends on whether we can learn to hear that rhythm and finally keep time. If there is one constant through all of Earth's history, it is renewal after imbalance. The planet has been through hotter times, colder times, and stranger atmospheres than this one, yet balance always finds a way back, not through miracle, but through persistence. The difference now is that the balancing agent could be us. For the first time in geological history, the species capable of disrupting a planetary system might also be capable of stabilizing it. It's an uncomfortable privilege. We are both the problem and the possible solution, the feedback and the fix. In laboratories, researchers are learning how to store wind in stone, how to trap the breath of machines and bury it beneath fossil seams. Engineers are experimenting with basalt injections that lock carbon into rock for millennia. In the oceans, tiny engineered kelp farms are designed to sink and take their captured carbon with them into the abyssal plain, becoming future geology. These experiments sound like science fiction, but so did flight and vaccines once. Each idea is a modern echo of the same planetary impulse, to recycle, to absorb, to begin again. And in that sense, the technology mirrors biology. Earth itself has always practiced carbon capture, just in slower ways. Shells, peat bogs, and limestone cliffs, all archives of the atmosphere's earlier versions. We're merely trying to accelerate what the planet already knows how to do. But perhaps technology is only half of the answer. The deeper shift might be psychological, learning to think in planetary rather than personal time. Most of our systems, from markets to politics, are built around immediacy. This quarter, this decade, this lifetime. Yet the planet's systems think in hundreds of years, in sediment layers and slow drifts of current. The mismatch between these tempos is where much of our anxiety lives. The long forecast asks something radical of us: patience. To act now, but to wait for the results we may never see. It is the same patience that glaciers once showed when carving valleys, or that forests practice when growing back after fire. Civilization has been many things: curious, restless, ingenious. Perhaps the next stage of its evolution is to become patient. Philosophers sometimes describe wisdom as the ability to hold two truths at once. For our species, those truths might be urgency and calm. The atmosphere is changing fast, yet our tools for repair require slow continuity. If we can find the balance between those scales, between emergency and endurance, we might begin to resemble the cycles that sustain us. It isn't about winning a war against nature. It's about learning to move in rhythm with it again. That rhythm is already written into our biology, in the beating of the heart and the breathing of the lungs. The same cadence that governs the tides in the magnetic field is mirrored inside us. If we can align those inner and outer tempos, our civilization might not just survive the Anthropocene but become its turning point, the era when intelligence learned to listen, not dominate. The sun will still rise and flare, the moon will still pull at the seas, the core will still turn beneath us. But maybe, after all our noise and heat, we will learn to exist as part of the music rather than the interruption. Thank you, fellow Sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the Sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.